There's something utterly humbling about staring up at the night sky, isn't there? That vast, endless expanse dotted with stars, each one a sun, each one a story. But what if I told you the universe holds sights far beyond what our eyes can see from Earth? Wonders so immense, so dazzling, they rewrite the rules of reality itself. Today, we're setting off on a voyage to uncover 42 cosmic vistas that don't just push boundaries, they shatter them. These aren't just pretty pictures, they're windows into the deepest mysteries of existence, where swirling nebulae paint the canvas of space and galaxies spin like cosmic whirlpools billions of light years away. Think about the last time something truly took your breath away. Now multiply that feeling by the scale of the universe. These celestial marvels aren't just beautiful, they're alive with science, each one a clue to the grand puzzle of how everything, from the tiniest atom to the largest galaxy, came to be. Some reveal the violent births of stars, while others whisper secrets about black holes so powerful they bend time itself. And here's the thing. Every time we peer deeper into the cosmos, we're not just discovering new places. We're discovering new possibilities. So why does this matter to you? Because these vistas aren't just out there, they're part of us. The same stardust that sculpts distant nebulae flows through our veins. The same forces that shape galaxies once shaped the conditions for life on Earth. This journey isn't just about awe, it's about connection. By the end of this video, you won't just see space differently, you'll feel it. From the fiery hearts of dying stars to the eerie glow of dark matter, we're about to explore the universe's most spectacular masterpieces. And trust me, you'll never look up at the night sky the same way again. Imagine standing before a cathedral of gas and dust so vast, its pillars stretch trillions of miles into the cosmic void. This is the Pillars of Creation, one of the most breathtaking sights the universe has to offer. Nestled deep within the Eagle Nebula, these colossal towers aren't just static sculptures. They're alive with motion, cradling newborn stars in their swirling embrace. When the Hubble Space Telescope first captured their image, it revealed textures so intricate they looked like brushstrokes from some celestial artist. Every knot and filament tells a story of gravity's patient work, pulling matter together over thousands of years until, like a match struck in the dark, new stars ignite. But here's the twist, these pillars might not even exist anymore. A violent supernova could have already torn them apart, their destruction racing toward us at the speed of light. What we're seeing is a ghost image, a cosmic postcard from the past. That's the magic of astronomy, we're time travelers, peering into eras long gone. And while the pillars' fate remains a mystery, their legacy endures. They've shown us how stars are born from chaos, how delicate balance and brute force shape the universe. Hidden within those dusty tendrils could be clues about our own origins, because every atom in our bodies was once forged in places like this. What makes this vista truly extraordinary isn't just its beauty, it's the questions it raises. How many generations of stars have risen and fallen within these towers? What undiscovered worlds might be forming there right now, invisible to our eyes? The Pillars of Creation remind us that the universe is never still. It's a workshop, a graveyard, and a cradle all at once. And as we gaze at this frozen moment in time, we're reminded that even the mightiest structures in space are fleeting, yet their light echoes across eternity. Now picture a celestial sombrero floating silently through the inky blackness of space, its broad brim a swirling disk of dust, its crown a blazing core of ancient starlight. This is the Sombrero Galaxy, a cosmic masterpiece so perfectly balanced it looks like it was sculpted by the steady hand of gravity itself. Seen edge on from our vantage point, its dark dust lanes ripple outward like concentric waves frozen in time, while its brilliant central bulge glows with the combined light of billions of stars. But what makes this galaxy truly extraordinary isn't just its striking silhouette. It's the invisible monster lurking at its heart. Hidden within that radiant core lies a supermassive black hole, a gravitational titan so powerful it dictates the dance of every star around it. Astronomers estimate its mass at nearly 1 billion times that of our Sun, a number so vast it bends the mind. Yet despite this cosmic heavyweight, the Sombrero Galaxy remains eerily symmetrical, its structure undisturbed by the chaos you'd expect from such a violent anchor. How does it maintain this perfect equilibrium? That's the puzzle that keeps scientists awake at night. Some theories suggest it's the result of a delicate merger, where two galaxies collided long ago and left behind this harmonious relic. Others propose it's a rare example of a galaxy that avoided the usual turbulence of cosmic evolution. What's even more fascinating is what the Sombrero might tell us about our own galactic home. Like a mirror held up to the distant future, it offers a glimpse of what the Milky Way could become, its spiral arms settling into a serene disk as it ages, its central black hole growing ever more dominant. But here's the twist: the Sombrero Galaxy is also a cosmic loner, drifting through a relatively empty patch of space with few neighboring galaxies to disturb its solitude. That isolation might be the secret to its pristine form, a reminder that in the universe, beauty often thrives in quiet places, and then there are the mysteries we can't yet explain. Why does this galaxy have such an unusually large halo of globular clusters, thousands of ancient star systems orbiting it like bees around a hive? What caused its dust lanes to align so perfectly, as if sketched by an artist's ruler? Every new observation peels back another layer, revealing clues about how galaxies grow, change, and sometimes defy expectations. The Sombrero doesn't just challenge our textbooks, it invites us to rethink what's possible in a universe that always has another surprise up its sleeve. So the next time you look up at the night sky, remember, somewhere out there, a galaxy shaped like a hat is spinning silently in the dark, carrying secrets we've only begun to unravel. It's a reminder that the universe loves variety, and that even in the vastness of space, perfection can emerge from the unlikeliest of places. The Crab Nebula isn't just a cosmic ghost, it's a heartbeat. 1,000 years ago, light from an exploding star reached Earth, so bright it outshone the moon and was visible even during the day. Today, that cataclysm lives on as this swirling tapestry of gas, stretching 11 light-years wide and pulsing with the rhythm of a neutron star spinning 30 times every second at its core. What makes this remnant extraordinary isn't just its violent birth, but how it continues to shape our understanding of the universe's most extreme physics. Those delicate filaments you see aren't static, they're racing outward at nearly 1,000 miles per second, carrying shock waves that accelerate particles to energies we still can't replicate on Earth. At the heart of this chaos sits the Crab Pulsar, a city-sized powerhouse with the mass of 2 suns crushed into a sphere no wider than Manhattan. Its magnetic field is so intense, it generates beams of radiation that sweep across space like a cosmic lighthouse, beams we detect as precise flashes of X-rays and radio waves with every rotation. But here's what's truly mind-bending. This pulsar isn't just a remnant, it's an engine. The energy it pumps into the surrounding nebula lights up the entire structure, powering glowing tendrils that reveal secrets about how stars recycle their material back into the cosmos. What happened here in 1054 wasn't just an ending, it was a transformation. When that massive star collapsed, it forged elements like gold and uranium in its final moments, scattering them into space where they'd eventually become part of New World. The shockwaves from that explosion still ripple through the nebula today, acting as natural particle accelerators that help scientists study how cosmic rays, those mysterious high-energy visitors from space, get their incredible speed. Even the nebula's eerie blue glow comes from a process we're still unraveling, where electrons spiral along magnetic field lines at nearly the speed of light. But perhaps the most profound lesson from the Crab is how destruction breeds creation. Those twisted filaments aren't just debris, they're incubators. The same forces that tore a star apart also seeded the nebula with complex molecules, the building blocks for future stars and planets. It challenges everything we thought we knew about stellar life cycles, showing how chaos and order exist side by side in the universe. Every time astronomers point telescopes at this swirling wreckage, they find something new, whether it's unexpected gamma-ray flares or clues about how neutron stars power some of the brightest explosions in the cosmos. So when you look at images of the Crab Nebula, you're not just seeing a beautiful aftermath. You're witnessing a cosmic engine still hard at work, a laboratory where nature conducts experiments we can barely imagine. It's proof that in space, even death isn't final, it's just another form of reinvention, a reminder that the universe thrives on transformation, and somewhere in that glowing cloud of wreckage could be the seeds of worlds yet to be born, carrying forward the legacy of a star that died a millennium ago. Gazing into the Helix Nebula feels like staring into the iris of a cosmic eye, a vast, swirling pool of color where a star exhaled its last breath into the void. Known as the Eye of God for its eerie symmetry, this planetary nebula isn't just a spectacle, it's a prophecy. What you're seeing is the fate awaiting our own sun 5 billion years from now, when it too will shed its outer layers in a final, radiant farewell. The intricate rings of glowing gas, stretching nearly 3 light-years across, aren't random chaos, they're the fingerprints of a dying star's last act of creation. What makes the Helix so mesmerizing isn't just its haunting beauty, but the precision of its destruction. As the star's core collapsed, it unleashed ultraviolet radiation so intense, it lit up the expelled gas like a neon sign in the cosmos. Those vibrant blues and reds, their elemental signatures: oxygen burning blue, nitrogen glowing red, painting a portrait of the star's final chemical symphony. And hidden in those luminous strands are microscopic structures scientists call cometary knots, each one a cosmic iceberg with a head of dense gas and a tail stretching trillions of miles. These peculiar formations might hold clues about how dying stars distribute the building blocks of planets and perhaps even life back into the galaxy. But here's what's truly humbling. The Helix's central white dwarf, the smoldering ember left behind, is still shaping its surroundings. Though only the size of Earth, it radiates enough energy to keep the entire nebula illuminated, a testament to the staggering density of stellar remnants. Over millennia, those glowing rings will dissipate into the darkness, leaving behind nothing but the cooling white dwarf, a silent sentinel of what once was. Yet even in this dissolution, there's rebirth. The same elements forged in the star's death, throws carbon, nitrogen, oxygen, will someday seed new stars, new worlds, new possibilities. The Helix Nebula challenges us to rethink endings. It's not a grave, it's a nursery. Those radiant gases are proof that in the universe, nothing is truly lost, only transformed. And as we study its intricate layers, we're learning how even average stars like our Sun can leave behind legacies far grander than their lifetimes. Every atom in those glowing tendrils is a messenger from the past, whispering secrets about the cycles that bind us all, star stuff to star stuff, from one cosmic generation to the next. There's something almost intimate about the Andromeda Galaxy, a colossal spiral of stars so close we can see its faint glow with the naked eye on clear nights. Stretching 200,000 light-years across and home to over 1 trillion stars, our nearest galactic neighbor isn't just a pretty sight. It's a time capsule, a mirror, and a harbinger all at once. Right now, Andromeda is racing toward the Milky Way at 250,000 miles per hour, setting the stage for the greatest cosmic collision our local universe will ever witness. But don't panic, this dance won't begin for another 4 billion years. What makes Andromeda extraordinary isn't just its inevitable merger with our galaxy, but what it reveals about how such giants evolve. Its spiral arms, studded with young blue stars and veined with dark dust lanes, show a structure eerily similar to our own Milky Way, yet with crucial differences. Andromeda's core is brighter, its halo more extended, and it's surrounded by a swarm of satellite galaxies that orbit like fireflies around a lantern. Some astronomers believe it may have already cannibalized smaller galaxies in its past, growing larger and more dominant over time. But here's the twist: when Andromeda and the Milky Way finally meet, it won't be the violent crash you might imagine. Galaxies are mostly empty space, so their stars will slide past one another like two swarms of bees merging without direct collisions. Gravity will stretch both galaxies into long, luminous streamers before slowly weaving them together over billions of years into a single, elliptical galaxy, dubbed Andromeda by scientists. The night sky from Earth, if any life remains to see it, will transform beyond recognition. Andromeda's spiral will swell from a faint smudge to a blazing disk, then gradually merge with the Milky Way into a chaotic tapestry of new stars and rearranged constellations. What fascinates researchers most are the clues Andromeda holds about our own galaxy's past and future. By studying its star clusters, we've learned that galaxies grow by absorbing smaller neighbors, a fate the Milky Way has likely already experienced multiple times. Its dust clouds reveal how raw materials for new stars differ slightly from ours, hinting at variations in cosmic chemistry across the local universe. Even its central supermassive black hole, though currently quiet, shows signs of past outbursts that may predict similar activity in our own galactic core. Yet mysteries remain. Why does Andromeda have a peculiar double nucleus at its heart? How did its outermost stars end up moving in the opposite direction from the galaxy's rotation? Each unanswered question reminds us that even our closest cosmic neighbor keeps secrets. But one thing is certain: when these two galaxies finally embrace, it won't be an ending, it'll be a rebirth. New stars will ignite from the stirred-up gas, planets may form in pristine environments, and the combined gravity will sculpt something entirely new from the wreckage. So the next time you spot Andromeda's faint glow in the autumn sky, remember, you're not just looking at another galaxy, you're seeing a future dance partner, a cosmic counterpart whose destiny is forever entwined with ours. It's a humbling reminder that even the mightiest structures in the universe are in motion, bound by gravity's patient pull toward an inevitable and spectacular union. The Orion Nebula isn't just another smudge in the night sky, it's a bustling maternity ward for stars, so close and bright you can spot it without a telescope. Suspended in Orion's sword, this cosmic cloud spans 24 light-years, a swirling canvas where gas and dust collapse under gravity's grip to ignite new suns. But what makes this stellar nursery truly special isn't just its visibility. It's the front row seat it gives us to the chaotic, breathtaking process of star birth. Peer into Hubble's images and you'll see tendrils of glowing hydrogen lit up like neon signs, sculpted by the fierce winds of newborn stars. Look closer and the details become even more astonishing. Protoplanetary disks, dense rings of material orbiting infant stars, dot the nebula like cosmic fingerprints. These aren't just abstract shapes, they're the birthplaces of future solar systems, where dust grains collide and stick together, slowly building the foundations of planets. Some of these disks already show gaps and spirals, telltale signs that young worlds might be carving their paths through the debris. The sheer variety is staggering, from massive stars blazing with ultraviolet light to tiny, dim red dwarfs that will outlive our sun by trillions of years. What's unfolding here isn't just a spectacle, it's a time machine. The Orion Nebula captures a phase of stellar evolution our own solar system passed through 4.5 billion years ago. Those violent jets of material shooting from young stars, their cosmic umbilical cords shedding excess energy as the stars grow, the dark, dusty globules hiding in the nebula's folds. Their cocoons shielding even younger stellar embryos from the harsh radiation around them. Every process we see here, accretion, outflows, fragmentation, mirrors the steps that once built our sun and its planets. Yet for all its beauty, the Orion Nebula is also a battleground. The Trapezium cluster, a group of brilliant young stars at its heart, floods the region with radiation so intense it's evaporating nearby gas clouds, limiting how long this nursery can keep forming stars. It's a reminder that creation and destruction go hand in hand in the cosmos. Even now, shockwaves from older stellar explosions ripple through the nebula, compressing gas and triggering new rounds of star formation. The most tantalizing question isn't whether planets are forming there. We know they are, but how many might resemble Earth? With over 700 young stars identified and countless more hidden in the dust, the possibilities are endless. Some disks show chemical signatures of water and organic molecules, the very ingredients that seeded life on our planet. Could there be worlds around these infant stars where oceans are just beginning to pool, where continents are still molten rock? We may never know for certain, but the Orion Nebula assures us of one thing: the universe is always building, always experimenting, turning stardust into new chances for wonder. Standing as both a laboratory and a gallery, this nebula doesn't just show us how stars are born, it shows us how we came to be. Every atom in our bodies, every mountain on Earth, every drop in our oceans was once part of a cloud like this, forged in the fires of stellar nurseries we can now see with our own eyes. That glowing patch in Orion's sword isn't just light years away. It's a piece of our origin story still being written. The Whirlpool Galaxy spins through space like a cosmic pinwheel, its arms unfurling in near-perfect symmetry, a masterpiece of celestial design that defies the chaos usually found in the universe. Located 23 million light-years away in the constellation Canes Venatusi, this grand design spiral isn't just a pretty face. It's a dynamic laboratory where gravity's invisible hand shapes entire ecosystems of stars. What makes the Whirlpool extraordinary isn't just its structure, but the fiery tango it's performing with a smaller companion galaxy, NGC 5195. Their gravitational dance stretches tendrils of gas and dust between them, triggering fireworks of Starburst that illuminate the secrets of galactic evolution. Look closely at those spiral arms, and you'll notice something surprising. They're not just smooth trails of stars. They're studded with pink knots, each one a stellar nursery where massive young stars blaze to life, their ultraviolet light ionizing surrounding hydrogen gas into glowing clouds. These regions aren't random. They trace the galaxy's density waves like cosmic traffic jams where gas piles up, cools, and collapses into new suns. But here's the twist: many of these star-forming hotspots owe their existence to the Whirlpool's gravitational partner. As the smaller galaxy tugs on its larger neighbor, It sends shock waves through the whirlpool's disk, compressing gas clouds and lighting the fuse for stellar explosions. This interaction offers a rare glimpse into how galaxies evolve through collisions, not destructive crashes, but slow, graceful mergers that can last billions of years. The Whirlpool's companion has already stripped away some of its outer stars, leaving behind a shimmering veil of tidal debris. Yet instead of tearing each other apart, their gravitational embrace is creating something new. The same forces that distort their shapes also seed future generations of stars, proving that in the cosmos, destruction and creation are two sides of the same coin. What's even more remarkable is how the Whirlpool challenges our assumptions about galactic lifespans. Its pristine spiral structure suggests it's younger than our own Milky Way, yet it's already undergoing the kind of interaction typically associated with older galaxies. Some astronomers believe its symmetrical arms might be a fleeting phase, destined to warp and twist as the merger progresses. Others speculate that its central black hole, though currently quiet, could awaken as more gas funnels toward the galaxy's core, a reminder that beauty in space often masks latent power. Hidden in the Whirlpool's swirling patterns are clues about our own galaxy's future. The Milky Way and Andromeda may one day resemble this pair, their spiral arms stretching into streamers as they begin their own billion-year waltz. But the Whirlpool also raises questions we're still struggling to answer. Why do some galactic collisions trigger frenzied star formation while others shut it down? How do spiral arms maintain their structure amid such turbulence? Every observation peels back another layer, revealing how galaxies like living things grow, adapt, and sometimes defy expectations. So the next time you see an image of the Whirlpool, remember, you're not just looking at a static snapshot. You're witnessing a slow-motion transformation, a celestial choreography where gravity writes the music and stars are the dancers. It's a reminder that even the grandest structures in the universe are never truly alone. They're part of an endless web of interactions, each one shaping the story of the cosmos in ways we're only beginning to understand. The Tarantula Nebula doesn't just form stars, it forges cosmic titans, stretching over 600 light-years in the Large Magellanic Cloud. This colossal stellar factory is the most active nursery in our galactic backyard, blazing with such ferocity that if it sat where the Orion Nebula is, its light would cast shadows on Earth. What sets the Tarantula apart isn't just its size, it's the extreme physics unfolding within its filaments. Here, stars don't just ignite, they erupt into existence with masses up to 300 times that of our Sun, defying what we thought possible about stellar birth. At its heart lies R136, a dense cluster where behemoth stars huddle like giants around a campfire. Their radiation is so intense, it carves cavities in the surrounding gas, creating towering pillars that resemble the legs of its namesake spider. These structures aren't static, they're battlegrounds where gravity and radiation duel. New stars condense in the shadows of these pillars, shielded long enough to grow before the very winds that sculpted them tear their nurseries apart. It's a paradox, destruction enabling creation, chaos fostering order. But the real marvel is how the Tarantula challenges our understanding of star formation. In most nebulae, massive stars are rare. Here, they're practically common. Astronomers suspect the nebula's unusually dense gas clouds allow gravity to pack more material into each stellar embryo, creating these record-breaking suns. And when such stars die, they don't fade quietly, they obliterate themselves in supernova so powerful, they can trigger waves of new star birth across the nebula like cosmic dominoes. Hidden in this maelstrom is an even greater enigma, 30 Doradus, a region so packed with young stars that their combined light outshines small galaxies. Some of these stars are so luminous, they emit over 1 million times the energy of our Sun, their surfaces hotter than 50,000 degrees. Yet for all their brilliance, their fleeting many will burn out in just a few million years, a blink in cosmic time. Their short, violent lives seed the nebula with heavy elements, enriching future generations of stars and planets. What makes the Tarantula truly humbling is its role as a time capsule. The Large Magellanic Cloud lacks the heavy elements common in our galaxy, mimicking conditions in the early universe. By studying this nebula, we're glimpsing how the first stars might have formed, colossal, tempestuous, and radically different from today's suns. It's a living relic of the cosmos' youth, showing us that the universe's creative power has always pushed boundaries. So when you see images of the tarantula's glowing tendrils, remember, you're not just looking at a nebula. You're witnessing the universe's laboratory for extremes, where the rules of star formation get rewritten. Every flicker of light from those distant giants carries a message about our origins, our place in the cosmos, and the untamed forces that shape existence itself. The Ring Nebula floats in space like a luminous smoke ring, a nearly perfect circle of glowing gas that defies the chaos usually found in stellar deaths. Located 2,000 light-years away in the constellation Lyra, this planetary nebula isn't just a celestial jewel, it's a textbook example of how average stars like our Sun bow out of the cosmic stage. What makes this vista extraordinary isn't just its symmetry, but the precision of its formation. When a star exhausts its nuclear fuel, it doesn't explode randomly. It sheds its outer layers in carefully sculpted waves, leaving behind a glowing shell so geometrically precise, it looks like it was drawn with a cosmic compass. Peer through a telescope, and you'll notice the ring's colors aren't uniform. The outer edges glow blue from ionized oxygen, while the inner regions shimmer red with hydrogen and nitrogen, a layered palette that reveals the star's final chemical fingerprint. But here's the twist: that iconic ring shape is an illusion of perspective. We're actually looking down the barrel of a three-dimensional bubble of gas, a structure more like a donut with its hole facing Earth. Hubble's sharper images reveal intricate tendrils and knots within the nebula, evidence of turbulence and magnetic fields shaping the star's final breath. At the heart of this glowing shell sits a white dwarf, the star's collapsed core. Though no larger than Earth, it burns at over 100,000 degrees, bathing the surrounding gas in ultraviolet light that makes the entire nebula fluoresce like a neon sign. This tiny ember is the engine behind the spectacle, proving that even in death, stars remain anything but passive. Over the next few thousand years, the ring will expand until it dissipates into interstellar space, but its legacy won't fade. Those glowing gases are rich with carbon, oxygen, and nitrogen, elements forged in the star's final acts that will someday seed new generations of stars and planets. What's truly humbling is how ordinary this process is. The Ring Nebula's progenitor star wasn't some cosmic giant. It was a sun-like star, unremarkable in life but breathtaking in its departure. That's the paradox of planetary nebulae. They're both common and spectacular, reminding us that even average stars can leave behind masterpieces. Their fleeting beauty, visible for only 10,000 years before fading, makes them rare snapshots of a universal process. Every atom in those glowing rings was once part of the star's atmosphere, now returned to the cosmos where it might one day become part of new worlds or even new life. The ring doesn't just show us how stars die, it shows us how they ensure their immortality. By scattering enriched material back into space, they become part of an endless cycle of creation. That faint glow in Lyra isn't just a relic, it's a promise that in the universe nothing truly ends. It just changes form, weaving the story of the cosmos one stellar farewell at a time. Cartwheel Galaxy spins through space like a celestial bullseye, It's concentric rings of blue-hot young stars rippling outward from a golden core, a cosmic ripple frozen in time. This isn't just another spiral galaxy. It's a forensic snapshot of a head-on collision, a galactic car crash played out over hundreds of millions of years. Roughly 400 million light-years away in the constellation Sculptor, the Cartwheel's bizarre structure tells the story of a smaller galaxy punching straight through its center, sending shockwaves through its gas clouds like a pebble dropped in a pond. The result, a ring galaxy so textbook perfect, it could be an astronomer's diagram come to life. What makes this vista astonishing isn't just the violence of its origin, but the creativity of its aftermath. Those radiant outer rings aren't static, they're wave fronts of star birth, where compressed gas collapsed into millions of new suns. The initial impact triggered a chain reaction. The first ring expanded outward at nearly 200,000 miles per hour, triggering a secondary ring behind it like concentric tsunamis of starlight. Meanwhile, the galaxy's original spiral arms, stretched and splintered by the collision, now dangle like broken spokes from the central hub, a ghostly reminder of what once was. But here's the twist: the Cartwheel isn't just a victim, it's a phoenix. The same collision that tore it apart also gave it new life. The intruder galaxy injected fresh gas into the system, fueling a starburst so intense that the Cartwheel now produces new stars at 30 times the rate of our Milky Way. Its brightest clusters, visible as blue knots along the rings, are stellar nurseries where suns ignite in dense packs, some so massive they'll explode as supernova within a few million years. This isn't destruction, it's reinvention, proving that in the cosmos, even catastrophe can spark creation. What fascinates scientists most are the clues the Cartwheel holds about galactic resilience. Despite the violence of the impact, its central bulge survived relatively unscathed, a testament to how densely packed old stars resist disruption. The galaxy's outer disk, however, became a canvas for gravity's artistry, stretched, folded, and sculpted into those iconic rings. By studying their precise shapes, astronomers can reconstruct the angle and speed of the collision like cosmic detectives piecing together a crime scene. Yet mysteries remain. Why did the collision produce such perfect rings instead of a chaotic mess? How long will the Cartwheel maintain this structure before gravity smooths it back into a more conventional shape? And most tantalizing of all, what happens to planetary systems during such collisions? While stars rarely collide due to the vast distances between them, the shockwaves could destabilize orbits, flinging planets into new trajectories or triggering comet showers that might seed life on otherwise frozen worlds. The Cartwheel Galaxy challenges us to rethink cosmic evolution. We once imagined galaxies as isolated islands growing slowly over eons. Now we see them as dynamic beings, shaped by encounters sometimes gentle, sometimes brutal. Its rings are more than just a pretty face. They're a living lesson in how the universe thrives on interaction. Every ripple tells a story of transformation, proving that even in the vastness of space, no galaxy is an island. So the next time you hear about galactic collisions, remember, they're not endings, they're rebirths. The Cartwheel's luminous loops are proof that chaos and beauty aren't opposites, they're partners in the cosmic dance, spinning new wonders from the wreckage of the old. And somewhere out there, another galaxy might be lining up for its own transformation, waiting to show us yet another way the universe reinvents itself. The Vale Nebula floats in space like a cosmic lace curtain, its delicate filaments glowing with the ghostly light of a star's final scream. Stretching 110 light-years across the constellation Cygnus, this sprawling supernova remnant is more than just debris. It's a forensic record of one of the most violent events in the universe. Roughly 10,000 years ago, a star 20 times more massive than our Sun, detonated with such force that its light would have outshone the crescent moon in Earth's night sky. Today, what remains is a labyrinth of ionized gas, its intricate loops and tendrils painted in hues of red and blue by hydrogen and oxygen atoms still trembling from the blast. What makes the Vale so mesmerizing isn't just its beauty, it's the physics etched into every strand. Those glowing filaments aren't random, they're shockwaves frozen in time, where the expanding debris slammed into interstellar gas at nearly 1,000,000 miles per hour. The nebula's famous Witch's Broom section reveals these collisions in exquisite detail, with thread-like structures so fine, they resemble brushstrokes from some celestial artist. But this isn't art, it's turbulence on a cosmic scale, showing how energy from the explosion cascades through space, heating and twisting matter into these haunting shapes. Hidden in these filaments is a paradox: destruction birthing creation. The same shock waves that tore the star apart also forged heavy elements like silicon, iron, and sulfur, scattering them into space where they'll someday form new stars, planets, and perhaps even life. The Vale's oxygen-rich knots glow particularly bright, a sign that the dying star cooked these elements in its core before catapulting them into the void. It's a reminder that the very atoms in our bones were once forged in explosions like this, making supernova not just endings, but essential chapters in the story of cosmic recycling. Yet the Vale holds mysteries we've only begun to unravel. Why do some regions glow predominantly red from hydrogen, while others shimmer blue with oxygen? The answer lies in temperature. The hotter regions excite oxygen atoms, while cooler areas allow hydrogen to dominate. But what created these variations? Astronomers suspect the original star wasn't just a uniform sphere. It may have had dense clumps or magnetic fields that channeled the explosion's energy unevenly, leaving this patchwork of color and structure. Perhaps most astonishing is how the Vale connects to us. Light from the supernova reached Earth just as human civilizations were transitioning from hunter-gatherers to farmers, meaning our ancestors may have witnessed this stellar death without understanding what they saw. Today, we can trace the explosion's aftermath in astonishing detail, watching as its shockwaves still push outward, interacting with other interstellar clouds and triggering new waves of star formation. The Vale isn't just a relic, it's an active participant in shaping its corner of the galaxy. So when you gaze at images of the Vale Nebula, remember, you're not just seeing wreckage. You're witnessing a stellar legacy, an explosion that rearranged its corner of the cosmos and seeded it with the ingredients for future worlds. It's proof that even in death, stars don't vanish. They transform, leaving behind echoes of their brilliance for millennia to come. And somewhere in those glowing tendrils, the universe whispers a truth we're only beginning to grasp. Creation and destruction are forever entwined, two sides of the same cosmic coin. The Triangulum Galaxy drifts through space like a cosmic time capsule, its spiral arms unbroken by violent collisions or the gravitational tantrums of larger neighbors. As the third largest member of our local group after Andromeda and the Milky Way, this serene island of stars offers something rare, a glimpse into how galaxies evolve when left to their own devices. Unlike its rowdier siblings, Triangulum's 50 billion stars spin in near-perfect harmony, its delicate structure untouched by the mergers that warp so many others. But don't mistake its tranquility for simplicity. This galaxy is a bustling workshop where stars are born at twice the rate of our own Milky Way, painting its arms with glowing nebulae and young blue clusters that sparkle like diamonds on velvet. What makes Triangulum so fascinating isn't just what it shows us, but what it doesn't. Its quiet existence challenges the assumption that galaxies must collide to thrive. While Andromeda and the Milky Way have grown by cannibalizing smaller neighbors, Triangulum's symmetrical arms suggest it's avoided such cosmic drama for billions of years. Yet paradoxically, it's far from dormant. Its heart pulses with star formation, particularly in the colossal nebula NGC 604, a stellar nursery so vast it outshines Orion's famous clouds by a factor of hundreds. This raises a tantalizing question. How does a galaxy stay so pristine while still churning out new stars at a prodigious rate? The answer might lie in its delicate balance of resources. Triangulum's gas reservoirs are unusually rich and well-distributed, feeding star birth without the disruptive bursts seen in galaxies that feast on mergers. Its spiral arms act like conveyor belts, gently channeling gas inward to sustain creation without the violent fits and starts that leave other galaxies lopsided or pockmarked with starbursts. Even its central black hole is remarkably well behaved, a lightweight compared to the monsters lurking in Andromeda and the Milky Way, exerting just enough gravity to maintain order without stirring up chaos. But Triangulum's serenity won't last forever. Astronomers have detected faint streams of stars at its edges, hints that it's beginning to feel the gravitational tug of Andromeda, its massive neighbor. In a few billion years, it may become a snack for the larger galaxy, its stars absorbed into Andromeda's halo. For now, though, it stands as a testament to the universe's quieter paths of evolution, proving that galaxies don't need drama to flourish. Hidden in its spiral arms are clues to another mystery: why some galaxies become stellar factories while others stagnate. Triangulum's star-forming regions are organized differently than ours, with massive clusters forming farther from the core, a pattern that might reveal how galactic environments shape the birth of stars. Its H2 regions, those glowing pockets of ionized hydrogen, are laboratories for studying how radiation from young stars carves cavities in gas clouds, triggering or quenching further star birth. Perhaps most humbling is what Triangulum tells us about perspective. From our vantage point, we see it nearly face-on, a perfect spiral floating against the blackness of space. But if we could stand on one of its outer planets, the view would be unrecognizable. The night sky ablaze with the light of its dense star fields, its nebulae so close they'd cast shadows. It's a reminder that the universe's beauty isn't just in the grand designs we observe from afar, but in the countless unseen vistas waiting within each galaxy, each cluster, each swirling cloud of cosmic dust. So while the Triangulum Galaxy may lack the fireworks of its neighbors, its quiet brilliance offers something equally precious, a masterclass in galactic grace, a demonstration of how equilibrium and creativity can coexist on the grandest scales. In its undisturbed arms, we find proof that the universe writes its stories not just in explosions and collisions, but in the patient, luminous unfolding of a spiral turning slowly through the dark. The Horsehead Nebula emerges from the cosmic canvas like a shadow puppet against a backdrop of fire, a silhouette so perfect, it's hard to believe nature carved it by chance. This iconic formation in Orion's belt isn't just a trick of perspective. It's a towering pillar of cold hydrogen and dust, stretching 3 light-years high and dense enough to blot out the fierce glow of the emission nebula behind it. But what makes this vista extraordinary isn't just its familiar shape, it's the quiet drama unfolding within those dark folds. That Inkai outline isn't empty, it's a cocoon. Inside, gravity is patiently knitting together molecules, building the foundations of future stars. Zoom in closer, and the Horsehead reveals its secrets. The nebula's famous profile is sculpted by stellar winds from nearby young stars, their radiation eroding the gas like a sandblaster carving rock. The rim of the main glows faintly with the reflected light of Sigma Orionis, a hot blue star whose ultraviolet rays ionize the surrounding hydrogen into a crimson curtain. Yet despite this bombardment, the Horsehead endures, a testament to the tenacity of cosmic dust. Over millennia, though, even this colossal structure will dissipate, its material either collapsing into new stars or scattering into space. That's the paradox of dark nebulae. They're both monuments and raw material, resisting destruction just long enough to give birth to something new. What's truly humbling is how much we don't see. The Horsehead silhouette dominates our view, but it's just one ripple in a vast ocean of dark clouds that stretch across Orion. These aren't voids, they're labyrinths of frozen molecules and complex organic compounds, some of the coldest, most pristine places in the galaxy. Within them, temperatures plunge to just 10 degrees above absolute zero, allowing molecules like carbon monoxide and formaldehyde to form icy mantles on dust grains. These ices are the building blocks of life, waiting for a stellar nursery to melt them into protoplanetary disks. The Horsehead also challenges us to look beyond the obvious. Its familiar shape grabs our attention, but the real magic lies in the subtleties, the way its base flickers with the faint infrared glow of embryonic stars, or how its neck bends under magnetic fields we're only beginning to map. Even the nebula's darkness is an illusion. Peer through radio telescopes, and it becomes a bustling highway of molecules, vibrating with the energy of collisions too faint for our eyes to see. So the next time you spot this cosmic steed in images, remember, you're not just seeing a shadow, you're witnessing a threshold, a boundary between light and dark where the universe's most delicate creations take shape. And who knows what other silhouettes lurk in the unexplored corners of space. Perhaps another nebula hides the profile of a dragon, a ship, or a face we'd recognize in an instant. The cosmos has a way of mirroring our imagination, reminding us that even in the grandest scales, there's room for familiarity and wonder. The Antennae galaxies spin through the cosmos like celestial partners in a gravitational tango, their once pristine spiral arms now torn into luminous streamers that stretch over 300,000 light-years across space. What makes this collision so mesmerizing isn't just its scale, it's the raw energy of creation unfolding in real time. These two galaxies, known individually as NGC 4038 and NGC 4039, have been locked in a slow-motion embrace for the past 300 million years, their stars weaving past one another like swarms of fireflies while their gas clouds slam together at millions of miles per hour. The result, a fireworks display of star birth so intense it outshines entire galaxies. Look closely at those arcing tails, dubbed antennae for their insect-like appearance, and you'll see them studded with ruby red knots. Each one is a stellar nursery where compressed gas ignites into clusters of newborn stars, some so massive they blaze with the light of a million suns. This isn't just a collision, it's a cosmic renaissance. The same forces tearing these galaxies apart are also seeding their future, proving that in the universe, destruction and creation are inseparable partners. What's truly astonishing is how ordinary this process is. While the Antennae's drama plays out 700 million light-years away, it's far from unique. Nearly all large galaxies, including our Milky Way, have grown through similar mergers. Computer simulations suggest the Antennae will eventually settle into a single elliptical galaxy, its spiral arms smoothed into a featureless halo, a fate that awaits our own galaxy when it collides with Andromeda billions of years from now. But here's the twist: these mergers don't just reshape galaxies, they reshape the universe's very chemistry. The Antennae's violent starbursts are forging heavy elements like gold and platinum, scattering them into space where they'll someday form rocky planets or even life. Yet for all the chaos, there's unexpected order. Despite thousands of stars being flung into the galactic tails, direct collisions between stars are vanishingly rare. Galaxies are mostly empty space, so their stars slide past one another like ghosts, their paths bent but not broken by gravity's pull. The real action happens in the gas clouds, where molecules collide, heat up, and collapse into new stars at a rate dwarfing anything seen in isolated galaxies. This frenzy won't last forever. Eventually, the gas will exhaust itself, leaving behind a galaxy rich in stars but too depleted to birth many more. The antennae also challenge our assumptions about time. Human lives are too short to perceive galactic motion, but here we see the process frozen mid-stride, offering a snapshot of a transformation that takes 1 billion years to complete. Those shimmering tails aren't static, they're dynamic rivers of stars, some of which will escape entirely, becoming intergalactic wanderers. Others will loop back as the galaxy's gravity eventually pulls them into the newly merged core. Hidden in this cosmic wreckage are clues about deeper mysteries. Why do some galactic collisions trigger quasars while others, like the Antennae, spark starbursts? How do supermassive black holes at their centers eventually find each other and merge? Each question reminds us that for all we've learned, galaxy evolution remains a puzzle with pieces still missing. So when you gaze at images of the Antennae galaxies, remember, you're not just seeing a collision, you're witnessing the universe's grand recycling program, where old structures break down to build something new. It's a reminder that change isn't just inevitable in the cosmos, it's essential, the engine that drives galaxies to grow, evolve, and sometimes, against all odds, create beauty from chaos. The Cat's Eye Nebula stares back at us from 3,000 light-years away, its glowing concentric rings and radiant tendrils forming a cosmic iris suspended in the void. This isn't just another planetary nebula. It's a Russian nesting doll of stellar demise, with 11 distinct shells of gas expanding outward like ripples from a stone tossed into a pond. What makes the Cat's Eye extraordinary isn't just its layered beauty, but the violent tantrums of its central star, which ejected material in fits and starts over 1,500 years, leaving behind a timeline of its death encoded in those luminous rings. At its heart lies a white dwarf so hot it burns at nearly 90,000 degrees, its ultraviolet radiation lighting up the surrounding gas like a neon sign. But the real mystery is the nebula's structure, those perfectly symmetrical loops interrupted by chaotic jets shooting perpendicular to the rings, as if the star couldn't decide between order and chaos in its final moments. Astronomers suspect these contradictions stem from a hidden companion star, its gravitational tugs yanking material into bizarre shapes as the dying sun convulsed. The result, a celestial bullseye with explosive outbursts frozen in time, each layer a chapter in the star's protracted farewell. What's truly astonishing is how recently this drama unfolded. The outermost shells date back barely 1,000 years, a blink in cosmic terms, while the innermost structures are still expanding at 15 miles per second. We're witnessing the aftermath of stellar death in what amounts to real time, a rare opportunity to study how planetary nebulae evolve from one decade to the next. Even now, the nebula's chemistry surprises us. Its gas contains bizarrely high amounts of nitrogen and helium, suggesting the star was far more massive than its remnant suggests, having shed much of its weight in violent preludes before the final act. But the Cat's Eye's greatest secret might be its knots, dense globules of gas strung along the rings like beads on a necklace. These aren't random clumps. They're shaped by magnetic fields into teardrop forms, some with comet-like tails streaming away from the central star. Similar structures appear in other planetary nebulae, hinting at universal processes we're only beginning to decipher. Some researchers believe these knots are the key to how complex molecules survive the star's death throes, acting as shields that protect organic compounds from destructive radiation. The nebula also challenges our assumptions about symmetry in space. Most dying stars eject material uniformly, creating simple, round nebulae. The cat's eye's intricate structure suggests its progenitor star spun rapidly or had a powerful magnetic field that channeled its ejections into those precise rings and jets. This isn't just a star dying, it's a star dying with style, its final breath sculpted by forces we're still unraveling. So when you gaze at the cat's eye, remember, you're not just looking at a pretty cosmic object. You're seeing the last dramatic performance of a star that refused to fade quietly, its encores etched in glowing gas for millennia, and hidden in those luminous layers could be clues about our own sun's fate, a reminder that even the most beautiful things in the universe are born from turbulence, and that endings, when viewed from the right perspective, can be dazzling. The Butterfly Nebula spreads its luminous wings across 3,000 light-years of space, a celestial Rorschach test painted in glowing gas, one of the most symmetrical and intricate deaths the universe has to offer. This bipolar planetary nebula doesn't just resemble a butterfly. It moves like one, its twin lobes of gas expanding outward at speeds exceeding 600,000 miles per hour, sculpted by the ferocious winds of a dying star at its heart. What makes this vista extraordinary isn't just its beauty, it's the physics behind those perfect wings. Unlike the chaotic explosions of supernova, the butterfly's structure is a masterclass in controlled chaos, where radiation and stellar winds carve gas into shapes so precise they look laser-cut. At the center of this cosmic artwork sits a white dwarf, once a star like our Sun, now a smoldering ember hotter than 200,000 degrees. Its ultraviolet radiation ionizes the surrounding gas, making the nebula fluoresce in vivid hues of blue and gold, while twin jets of material shoot perpendicular to the wings like exhaust from a cosmic engine. But here's the twist: those iconic wings didn't form all at once. They're the result of multiple eruptions where the star shed its outer layers in pulses over thousands of years. Each ejection collided with previous ones, creating shockwaves that molded the gas into those ethereal curves. It's like watching a potter shape clay, except here, the sculptor is gravity, radiation, and time. The secret to the butterfly symmetry might lie in what we can't see. Astronomers suspect the presence of a companion star or a dense disk of material around the central white dwarf, funneling eruptions into opposing jets like water forced through a nozzle. This would explain not just the nebula's bipolar shape, but the intricate textures within each wing, delicate filaments and knots that reveal where fast-moving gas plowed into slower-moving clouds. Some regions glow brighter where elements like oxygen and nitrogen dominate, painting chemical fingerprints of the star's final nuclear reactions. What's truly humbling is how fleeting this masterpiece is. The butterfly's wings will continue expanding for just a few thousand more years before dissipating into interstellar space, a blink in cosmic time. Yet even as it fades, its legacy endures. The same heavy elements forged in the star's death, throws carbon, nitrogen, oxygen, will seed future generations of stars and planets. Those glowing wings aren't just debris, they're the building blocks of tomorrow's cosmos. But the Butterfly Nebula isn't just a relic, it's a laboratory. By studying its structure, scientists are unraveling how stellar winds interact with magnetic fields, how shockwaves trigger secondary star formation, even how planetary nebulae contribute to the galactic ecosystem. Its symmetry challenges assumptions about how chaos can birth order, proving that even in the violent throes of stellar death, the universe has a flair for elegance. So when you gaze at images of this cosmic butterfly, remember, you're not just seeing a dying star, you're witnessing a metamorphosis where one ending becomes the raw material for countless new beginnings. And somewhere in those radiant wings, the universe whispers a truth as old as time. Destruction and creation are forever entwined, each giving meaning to the other in an endless celestial dance. The Black Eye Galaxy glares across space like a cosmic cyclops, its luminous spiral arms sweeping around a nucleus half-shrouded by an ominous dark band, a thick river of dust so dense it swallows starlight whole. Located just 17 million light-years away in the constellation Coma Berenices, this striking galaxy isn't just a pretty oddity, it's a puzzle wrapped in shadow. That infamous dark lane isn't merely obscuring the core, it's a bustling highway of cold molecular gas and dust, the raw materials for future stars. But here's the twist. While the dust appears pitch black in visible light, infrared telescopes reveal it's anything but dead. Hidden within those shadowy tendrils are stellar nurseries, their newborn stars flickering to life behind the veil. What makes the Black Eye so captivating isn't just its contrast, but the mystery of how that dust lane formed. Most spiral galaxies distribute their dust evenly across their arms like sprinkles on a donut. The Black Eye's dust, however, is concentrated in a single, jagged band, as if a cosmic hand dragged a paintbrush dipped in soot across its face. Astronomers suspect a close encounter with another galaxy may have funneled gas and dust into this peculiar arrangement, stirring up the galaxy's disk like cream swirling in coffee. Yet despite this disruption, the Black Eye maintains near-perfect spiral symmetry beyond its darkened eye, a testament to gravity's ability to restore order after chaos. Peering deeper into that dust lane reveals even stranger secrets. Radio observations show it's not just passive debris, it's a dynamic structure, with filaments and knots where gravity is pulling material into dense clumps. Some of these clumps glow faintly in sub-millimeter wavelengths, betraying the heat of protostars buried too deep for visible light to escape. This hidden activity challenges assumptions about where and how stars can form, proving even the darkest corners of galaxies can harbor creation. But the real enigma is the galaxy's core. Behind that dusty curtain lies a region of intense star birth, where clusters ignite in bursts so bright they'd outshine the rest of the galaxy if not for the dust dimming their glow. Meanwhile, the supermassive black hole at the Black Eye's heart remains oddly quiet, unlike the blazing behemoths in other galaxies. This combination of a vibrant stellar nursery and a sleeping giant raises questions about how galactic cores evolve, and whether dust lanes like this might act as cosmic mufflers, stifling a black hole's appetite. What's most humbling is realizing this isn't just a distant curiosity, it's a mirror. Our own Milky Way has its own dust lanes, though none as dramatic as the Black Eye's. Studying this galaxy helps us understand how such structures shape a galaxy's life cycle, channeling gas toward the center to feed stars and black holes or blocking radiation that might otherwise halt star formation. Those dark ribbons aren't obstacles, they're architects quietly shaping their galaxies from within. So the next time you see an image of the Black Eye Galaxy, don't just focus on what's hidden. Consider what that darkness makes possible: the stars it shelters, the mysteries it preserves, and the reminder that even in the brightest places, the universe keeps its secrets tucked away in shadow. And somewhere in that Inkai band, there's likely a story we've only begun to read. The Omega Nebula blazes across the night sky like a celestial wildfire, its billowing clouds of gas sculpted into eerie shapes by the relentless winds of newborn stars. Stretching 15 light-years wide in the constellation Sagittarius, this stellar nursery isn't just another pretty cosmic cloud, it's a pressure cooker of creation, where stars ignite so violently they reshape the very nebula that birthed them. What makes this vista extraordinary isn't just its radiant glow, but the way it lays bare the turbulent relationship between stars and their cribs. Those dark tendrils weaving through the nebula aren't empty voids. They're dense cocoons of dust, shielding the next generation of stars from the very radiation that's tearing the surrounding gas apart. At the heart of the Omega Nebula lies a cluster of young, massive stars, each one a furnace burning tens of thousands of degrees hotter than our Sun. Their ultraviolet light ionizes the surrounding hydrogen gas, making it fluoresce in vivid pinks and reds, while their stellar winds carve cavernous bubbles into the nebula's structure. This isn't a peaceful nursery, it's a battleground where gravity and radiation wage war. The same stars that illuminate the nebula are also eroding it, their energy pushing against the gas clouds that once nurtured them. It's a cosmic paradox. The more these stars shine, the faster they destroy their own birthplace. Yet within this chaos lies a delicate balance. The nebula's famous horseshoe shape, visible even through small telescopes, isn't static. It's a dynamic structure where new stars continue forming even as the old ones disrupt their environment. Infrared observations reveal protostars buried deep within the darkest filaments, their growth shielded by dust from the very radiation that might otherwise stifle them. Some of these infant stars are already launching jets of material, narrow streams of gas shooting outward at hundreds of miles per second, like umbilical cords severed by the violence of birth. What fascinates astronomers most is how the Omega Nebula demonstrates stellar feedback on a grand scale. The massive stars at its core don't just light up the gas, they trigger chain reactions. Their radiation compresses nearby gas clouds, accelerating the formation of additional stars in a process called triggered star formation. Meanwhile, their eventual supernova explosions still millennia in the future will blast heavy elements back into the nebula, enriching it with the raw materials for planets and perhaps even life. This isn't just a snapshot of star birth, it's a glimpse at the cyclical nature of cosmic evolution. The Omega Nebula also holds clues about how star formation differs across the universe. Its massive stars are rarity. Most nebulae produce far smaller, cooler stars like our Sun. Yet here, conditions conspire to create stellar giants, suggesting that subtle variations in a nebula's density, temperature, or magnetic fields can dramatically alter its offspring. Some theories suggest the Omega Nebula's unique shape, its curved omega or swan profile, may be evidence of past collisions between gas clouds, creating pockets of extra density where massive stars could take root. But perhaps the most humbling lesson from the Omega Nebula is one of perspective. From our distant vantage point, its glow appears serene, a soft watercolor smudge in the Milky Way. Up close, it's a maelstrom of forces beyond human comprehension, where temperatures range from near absolute zero in the dust clouds to millions of degrees in stellar atmospheres. Its beauty masks violence, its tranquility belies chaos, and somewhere in those swirling gases, the same processes that forged our Sun and planets are unfolding anew, a reminder that the universe is always creating, always destroying, always writing new chapters in the story of stardust. So when you gaze upon the Omega Nebula's luminous curves, remember, you're not just seeing a cloud in space, you're witnessing a cosmic classroom where the most fundamental lessons of stellar life cycles play out on a scale so vast, it redefines our understanding of beginnings and endings. And hidden in its glow is a truth as old as time that light cannot exist without shadow, and creation cannot exist without destruction. The Pinwheel Galaxy spins through the void like a cosmic carousel, its arms unfurling in near-perfect symmetry against the velvet blackness of space. Known formally as Messier 101, this face-on-spiral galaxy is so large and close, just 21 million light-years away, that its intricate structure reveals itself in stunning detail. Each of those luminous arms is a stellar highway lined with young blue star clusters, glowing pink nebulae, and dark dust lanes that twist outward from a brilliant core. But what makes the pinwheel truly mesmerizing isn't just its beauty, it's the delicate equilibrium that keeps this cosmic pinwheel spinning gracefully, defying the chaos that should, by all rights, tear it apart. At first glance, the pinwheel's symmetry seems impossible. Galaxies are dynamic beasts, their stars and gas clouds constantly tugged by gravity, radiation, and collisions. Yet here, the spiral arms maintain an almost mathematical precision, their curves tracing what astronomers call a grand design pattern, a rarity among spirals which often appear flocculent or ragged. The secret lies in density waves, a phenomenon where spiral arms aren't fixed structures but moving traffic jams of stars and gas. As material orbits the galaxy's center, it piles up in these waves like cars slowing on a highway, compressing gas clouds until they collapse into new stars. The brightest regions mark where this process is most intense, creating the galaxy's beaded necklace of star clusters. But the pinwheel's balance isn't just about gravity. Magnetic fields thread through its disk like invisible wires, channeling gas and influencing how stars form. Its central bulge, though smaller than many spirals, acts as an anchor, its collective gravity helping to maintain the arm's coherence. Meanwhile, the galaxy's rotation, a slow, stately waltz that takes hundreds of millions of years to complete, spreads out disturbances, preventing any single force from overwhelming the system. It's a cosmic dance of push and pull where chaos and order find an uneasy truce. What's even more astonishing is how active the pinwheel remains. Most galaxies this symmetrical are relatively quiet, their star-forming days behind them. Yet here, the arms blaze with newborn stars, their intense radiation ionizing surrounding hydrogen into crimson nebulae. Some of these stellar nurseries are so massive, they rival the Tarantula Nebula in scale, churning out stars at a rate that dwarfs our Milky Way's output. This raises a tantalizing question. How does the pinwheel sustain such vigor without losing its shape? The answer might lie in its interactions with smaller satellite galaxies, whose gentle gravitational nudges could be funneling fresh gas into the spiral arms, fueling ongoing creation. Hidden within this apparent perfection are clues to deeper mysteries. The pinwheel's core glows unusually bright in X-rays, hinting at a supermassive black hole that's actively feeding, though not as voraciously as the monsters in some galaxies. Its outer arms show signs of warping, suggesting past encounters with neighboring galaxies that left subtle scars. Even its rotation curve, the speed at which stars orbit the center, deviates slightly from predictions, a whisper of dark matter's invisible hand shaping the galaxy from within. Yet for all we've learned, the pinwheel still guards its secrets. Why do some of its spiral arms appear to branch or fray at the edges? What determines which gas clouds collapse into stars and which remain dormant? Each observation peels back another layer, revealing how a galaxy's structure emerges from countless local interactions, like a murmuration of starlings forming shapes no single bird could plan. So when you gaze at images of the Pinwheel Galaxy, remember, you're not just seeing a static spiral, you're witnessing a dynamic equilibrium where gravity, magnetism, and motion conspire to create order on a scale so vast it defies intuition. It's a reminder that even in the cosmos where forces vie for dominance, there can be harmony fleeting, fragile, and utterly magnificent. The Rosette Nebula blooms in the cosmos like a celestial flower, its petals of glowing gas stretching 130 light-years across the constellation Monoceros. This isn't just a pretty cosmic accident, it's a dynamic workshop where stars are both the artists and the artwork, sculpting their birthplace with fierce stellar winds. At its heart lies NGC 2244, a young star cluster so bright, its radiation has blown a vast cavity in the surrounding hydrogen cloud, creating the nebula's iconic rose-like shape. What makes this vista extraordinary isn't just its beauty, but the way it reveals stars as architects of their own environments, shaping the very structures that birthed them. Those delicate filaments of gas aren't passive decorations, they're battlefronts. The cluster's hottest stars emit ultraviolet light so intense, it strips electrons from hydrogen atoms, making the nebula glow crimson. Meanwhile, their stellar winds particle streams moving at millions of miles per hour carve into the gas like cosmic sandblasters, pushing it outward into intricate loops and pillars. The result is a delicate balance, destruction enabling creation. As the central cavity expands, it compresses surrounding gas, triggering new rounds of star formation along the nebula's edges. It's a self-perpetuating cycle where one generation of stars prepares the nursery for the next. Hidden within the Rosette's folds are clues to stellar infancy. Infrared telescopes pierce the nebula's dusty veil, revealing protostars still swaddled in their gas cocoons, some so young they haven't begun nuclear fusion. These stellar embryos huddle in the shadow of their older siblings, sheltered from the radiation that would otherwise rip them apart. The nebula's darkest patches aren't empty, they're incubators where gravity patiently weaves molecules into new suns. Yet the Rosette's floral symmetry is fleeting. Over millennia, the central cluster's radiation will erode the nebula entirely, dispersing its gas into interstellar space. Those same stars that sculpted this cosmic rose will ultimately destroy it, a reminder that in the universe, beauty and transience are intertwined. What remains will be an open cluster of stars, their shared motion betraying their common origin, while the nebula's scattered atoms journey onward to fuel future creations. This celestial blossom challenges us to see the cosmos differently. If stellar winds can carve a rose in monoceros, what other floral wonders might lurk in the depths of space? From the tulip-shaped nebulae in Cygnus to the daisy-chain galaxies spun by tidal forces, nature's artistry transcends scale. The Rosette whispers a truth as old as time. The universe doesn't just build, it embellishes, crafting beauty from the chaos of creation. And somewhere in its glowing petals, we catch a glimpse of our own origins, forged in similar stellar nurseries billions of years ago. The Tadpole Galaxy drifts through the cosmic deep like a celestial lava, its once pristine spiral form stretched into a lopsided anomaly by the gravitational pull of an unseen interloper. This distorted galaxy, officially known as UGC 10214, isn't just a cosmic oddity, it's a living textbook on galactic evolution. Its 280,000 light-year long tail of stars painting a vivid picture of the universe's relentless reshaping forces. What makes this vista extraordinary isn't just its peculiar silhouette, but the story it tells about how even the mightiest structures in space are vulnerable to gravity's invisible hand. That dramatic tail, a streamer of stars and gas longer than our entire Milky Way, is no static scar. It's a dynamic river of stellar orphans, each one stripped from the tadpole's disk during a close encounter with a smaller galaxy some 100 million years ago. As the intruder tore through the tadpole's outskirts, gravitational tides pulled stars outward like taffy, leaving behind this glittering trail that now stretches across intergalactic space. The process wasn't violent collisions, but slow, inexorable tugs, gravity's patient unraveling of order into chaos. Yet within that chaos lies creation. The tail's densest knots are now incubators for new star clusters, proving that even in disruption, the universe finds ways to build. What's truly astonishing is how perfectly the tadpole captures a fleeting phase. Most galactic interactions last billions of years, but this one's aftermath is visible for just a cosmic blink before the tail dissipates or gets reabsorbed. We're witnessing a rare moment of transformation, like catching a butterfly mid-metamorphosis. The galaxy's distorted spiral arms, now asymmetrical and warped, show how these encounters don't just rearrange stars, they rewrite a galaxy's entire structure. The tadpole's core remains intact, its central bulge of ancient stars stubbornly resisting disruption, while its outer disk bears the brunt of the collision, a reminder that galactic centers are anchors in the storm. Hidden in this cosmic tadpole's tail are clues to deeper mysteries. The mix of young blue star clusters and older red stars suggests these gravitational encounters don't just scatter stars, they trigger new rounds of star formation as gas clouds compress during the chaos. Some of these newborn stars will eventually become unbound, wandering intergalactic space as orphans, perhaps the explanation for the rogue stars we've observed far from any galaxy. Others may form a new satellite galaxy, turning the predator into the prey as the tail's material coalesces under its own gravity. The tadpole also challenges our assumptions about galactic resilience. Computer simulations suggest it will never regain its original spiral form. Instead, it may become an irregular galaxy, its structure forever altered by this ancient encounter. This raises a humbling question: how many of the universe's normal galaxies were once like the tadpole, their violent past smoothed over by time? Our own Milky Way shows signs of past mergers, its halo littered with stellar streams, proof that no galaxy evolves in isolation. So when you gaze upon the tadpole galaxy's stretched silhouette, remember, you're not just seeing a galactic oddity, you're witnessing the universe's endless reconfiguration, where gravity's slow dance transforms spirals into sculptures. And somewhere in that glittering tail lies a message that even in the vastness of space, no galaxy is an island, and every collision writes new chapters in the story of cosmic evolution. The Flame Nebula flickers against the darkness like a cosmic campfire, its tendrils of hydrogen gas glowing orange and blue under the harsh ultraviolet light of nearby young stars. Situated in Orion's belt just below the leftmost star, Alnitak, this vast cloud isn't actually burning. It's a stellar nursery where gravity and radiation wage a relentless tug of war. The illusion of fire comes from ionized hydrogen, its atoms excited by the energy of massive stars like Alnitak itself, which bathes the nebula in radiation 20,000 times more intense than our sun's. What looks like smoke rising from the flames, dark lanes of interstellar dust, so dense they block the nebula's light, carving intricate patterns that resemble charred wood grain in a dying fire. Peering deeper reveals the nebula's true nature. Those dramatic ridges and folds aren't random, they're shock fronts where stellar winds collide with cooler gas, compressing it into new stellar embryos. Infrared observations pierce the dust, uncovering hundreds of protostars hidden within the nebula's darkest recesses. Some are barely more than knots of gas, while others have already ignited nuclear fusion, their fierce winds beginning to carve cavities in the surrounding cloud. This interplay of creation and erosion creates a dynamic equilibrium. As new stars emerge, their energy disperses the very material that birthed them, a cycle as old as the galaxy itself. What's most mesmerizing about the flame isn't just its glow, it's the contrast. The nebula's fire exists mere light years away from the Horsehead Nebula's Inkai silhouette, a reminder that light and shadow in space are often neighbors. Alnitak's radiation doesn't just illuminate, it sculpts, eroding nearby clouds into pillars that resemble stalagmites in a cosmic cavern. These structures, though seemingly solid, are ephemeral, their forms shifting over millennia as stellar winds reshape the gas-like sand dunes in a hurricane. The flame also challenges our earthly perspectives. From our vantage point, the nebula appears two-dimensional, a flat painting on the celestial canvas. In reality, it's a sprawling three-dimensional labyrinth where distances are deceptive. The stars we perceive as neighbors might be light years apart, their alignment a trick of perspective. This cosmic parallax creates illusions everywhere we look. Constellations that seem connected but aren't, nebulae that appear small yet span dozens of light years, even colors that shift based on the chemical composition of intervening dust. Hidden in the flame's flickering light are clues to stellar adolescence. The nebula's mix of mature stars and infant protostars offers a timeline of star formation, showing how siblings born from the same cloud can age at wildly different rates. Some of its youngest stars are still swaddled in dusty cocoons, while others have already blown away their birth shrouds, their radiation now ionizing the gas around them. This diversity makes the flame a living laboratory where astronomers can study every phase of stellar childhood in one luminous tableau. So when you gaze at the flame nebula's eerie glow, remember, you're not just seeing a pretty illusion. You're witnessing the universe's grand theater of light and shadow, where radiation paints masterpieces on clouds of cold gas. And somewhere in that false fire, reality burns even brighter, a reminder that the cosmos delights in disguising its truths, inviting us to look closer, think deeper, and marvel at the wonders hidden in plain sight. The silver coin galaxy gleams in the depths of space like a celestial treasure, its nearly edge on orientation revealing a razor-thin disk bisected by dark, swirling dust lanes. Officially catalogued as NGC 2537, this spiral galaxy's polished appearance has made it a darling of backyard astronomers. Its compact core and symmetrical profile so crisp, it resembles a freshly minted coin suspended in the cosmic void. But what makes this vista extraordinary isn't just its photogenic tilt. It's how this perspective unveils hidden dimensions of galactic structure that face-on views conceal. Those in-kite dust lanes aren't mere decoration. They're the skeleton of the galaxy, tracing spiral arms packed with cold molecular gas where future stars will ignite. Seen edge-on, their true thickness becomes apparent, a staggering 1,000 light-years deep in places, enough to obscure entire star clusters from view. This vantage point also lays bare the galaxy's vertical architecture. Unlike the flat disks often depicted in illustrations, the silver coin's profile reveals a subtle puffiness, its stars distributed in a lentil-shaped volume that hints at ancient collisions or turbulent magnetic fields shaping its evolution. The core glows disproportionately bright, its concentrated starlight suggesting a recent burst of star formation, or perhaps the gravitational influence of a central black hole too faint to detect directly. Meanwhile, the outermost regions fade into a gossamer halo of ancient stars, relics from the galaxy's violent youth, when smaller neighbors were torn apart and assimilated into this growing cosmic metropolis. What's truly revelatory is how much our understanding of galaxies depends on perspective. Had we evolved in a planet orbiting one of the silver coin stars, our night sky would look radically different. Instead of seeing it edge on as a slender streak, we might gaze directly into its spiral arms, where nebulae and star clusters would dominate the view like jewels scattered on black velvet. The dust lanes that appear as dark slashes from our vantage would instead be vast, three-dimensional labyrinths, not just shadows but structures with depth and texture capable of hiding entire stellar nurseries. This thought experiment underscores a humbling truth. Every galaxy image we admire is just a single frame in a cosmic flipbook. its appearance dictated by the accident of our viewing angle. The silver coin also challenges assumptions about galactic uniformity. Its dust lanes exhibit bizarre kinks and asymmetries, evidence of past gravitational encounters with unseen dwarf galaxies, or perhaps the lingering scars of internal instabilities. Some regions appear backlit by the galaxy's core, their silhouettes revealing complex filamentary structures that resemble frosted glass. These details, invisible in face-on views, testify to the dynamic processes shaping even seemingly tranquil galaxies. Hidden in this tilted vista are clues to broader mysteries. The way starlight polarizes as it passes through the dust lanes helps astronomers map magnetic fields weaving through the disk invisible forces that may dictate how gas collapses into stars. The subtle flaring of the galaxy's outer edges hints at the gravitational influence of dark matter, its invisible halo tugging the visible stars into unexpected configurations. Even the color gradient from the yellowish core to the bluer rim tells a story of stellar demographics, where ancient suns cluster near the center while younger, hotter stars dominate the outskirts. So the next time you spot the silver coin galaxy in telescopic images, remember, you're not just seeing a pretty spiral, you're peering through a keyhole into the third dimension of galactic structure, where perspective transforms flat portraits into living, breathing architectures. It's a reminder that the universe reveals its secrets reluctantly, offering fragmented views that we must stitch together one angle, one wavelength, one revelation at a time. And somewhere in that gleaming edge on disk lies an invitation to look deeper, to question our assumptions, and to wonder what other cosmic truths might be hiding in plain sight, waiting for the right angle to bring them into view. The Witchhead Nebula stares back at us from the constellation Orion, its wispy tendrils of dust and gas forming a spectral profile that could have leapt straight from a storybook. Illuminated by the brilliant blue supergiant Rigel, one of Orion's brightest stars, this reflection nebula doesn't emit its own light. Instead, it acts like a cosmic mirror, scattering Rigel's intense radiation into an eerie, ethereal glow. The result is a celestial Rorschach test, a face with a hooked nose, a gaping mouth, and hollow eyes frozen mid-scream against the velvet darkness of space. But what makes this vista extraordinary isn't just its haunting resemblance to a folklore, it's the delicate physics behind the illusion. Every twist of dust, every contour of gas is shaped by starlight itself, a reminder that even the most familiar shapes in the cosmos are born from impersonal forces of radiation and gravity. The nebula's blue hue isn't just for show. It's a fingerprint of Rigel's scorching 20,000-degree surface. Blue light scatters more efficiently off dust grains than red light, the same phenomenon that paints Earth sky blue. Yet, unlike our atmosphere, the Witchhead's dust particles are laced with carbon and silicates, their microscopic surfaces pitted and uneven. These imperfections act like celestial prisms, bending and reflecting light in unpredictable ways. Over centuries, Rigel's steady bombardment has sculpted the nebula's finer details, etching filaments so thin they'd vanish if viewed up close. It's a fleeting masterpiece, one that will dissipate long before Rigel exhausts its fuel, a whisper of dust destined to fade into the interstellar void. But the Witchhead's true magic lies in its duality. To the ancients, such formations were portents or deities. To modern astronomers, their laboratories for studying lights dance with matter. The same nebula that sparks campfire tales of supernatural hags also reveals how starlight pushes dust grains into alignment, creating polarization patterns that map magnetic fields threading through the cloud. These invisible forces guide the nebula's evolution, channeling energy into tendrils and voids that defy randomness. Even the face we recognize isn't static over millennia. Stellar winds from Rigel will erode and reshape it, leaving future civilizations to wonder what cosmic pareidolia they might glimpse in its remnants. This nebula challenges us to reconsider how we project meaning onto the cosmos. From the man in the moon to the constellations themselves, humans have always sought familiar patterns in the stars. The Witchhead is no different, a cosmic canvas where science and storytelling collide. But beyond the myth, it invites a deeper question. What other ghostly figures lurk in the depths of space, unseen simply because no one has looked at them from the right angle? Nebulae like the Soul, the Ghost of Cassiopeia, or even the Halloween Pumpkin Nebula prove that the universe has a flair for the dramatic, sculpting gas into shapes that ignite our imagination as much as our curiosity. Perhaps most humbling is the realization that these apparitions are temporary. The Witchhead's profile, so vivid in telescopic images, is already dissolving, its dust grains slowly dispersed by radiation pressure or absorbed into future generations of stars. One day, Rigel itself will explode as a supernova, its final blast likely vaporizing what remains of this eerie silhouette. But for now, it stands as a testament to the universe's quiet artistry, a reminder that even in the cold vastness of space, light and dust can conspire to create something hauntingly familiar. And somewhere in that gaseous visage there's a lesson. The cosmos reflects back not just what we see, but what we're willing to imagine. The Sculptor Galaxy blazes across the southern sky like a cosmic forge, its spiral arms crackling with the energy of newborn stars igniting at a frenetic pace. Unlike the stately pinwheels we often picture, this galaxy is a starburst, a celestial maelstrom where stars form 10 times faster than in our Milky Way, painting its core with the brilliant blue light of youthful stellar giants. What makes this vista extraordinary isn't just the spectacle, it's the violent backstory behind this creative frenzy. The Sculptor Galaxy isn't working alone. Its explosive productivity is fueled by a gravitational dance with smaller neighbors, their invisible tugs stirring up reservoirs of gas like a spoon swirling cream into coffee. Peer into its heart and you'll find a scene of controlled chaos. Dense molecular clouds compressed by the galaxy's interactions collapse into stars so rapidly they outshine their surroundings. The brightest clusters, some only a few million years old, already contain stars dozens of times more massive than our Sun, their ultraviolet radiation ionizing surrounding hydrogen into glowing crimson nebulae. This isn't gentle stargazing material, it's astrophysical theater where gravity's nudges trigger chain reactions that reshape entire galactic ecosystems. But here's the twist, these starbursts aren't sustainable. The Sculptor Galaxy is burning through its gas reserves at an unsustainable rate, like a wildfire consuming its fuel in one spectacular blaze. Within a few 100 million years, a mere blink in cosmic time, this frenzy will subside, leaving behind a galaxy littered with stellar remnants and the heavy elements forged in its furnaces. That's the paradox of starburst galaxies. Their most luminous eras are also their most fleeting, a reminder that cosmic creativity often thrives on borrowed time. What's truly fascinating are the fingerprints of interaction etched into the galaxy's structure. Faint streams of stars arc away from its disk, tidal tails left behind by past encounters, like breadcrumbs marking a gravitational trail. The precise arrangement of these features lets astronomers reconstruct the galaxy's history, revealing how a close pass with a smaller companion galaxy millions of years ago sent shockwaves through its gas clouds, compressing them just enough to ignite the current starburst. Its celestial cause and effect written in starlight, hidden in this frenzy, are clues to deeper mysteries. Why do some galactic collisions trigger starbursts while others shut down star formation entirely? The answer might lie in the angle of impact. Head-on collisions tend to funnel gas toward galactic centers, creating fireworks like those in the Sculptor Galaxy, while glancing blows can strip gas away entirely. There's also the role of dark matter, whose invisible halos around galaxies influence how they interact, steering them into orbits that maximize or minimize chaos. The Sculptor Galaxy doesn't just show us stellar creation, it reveals how galaxies communicate. Its starburst is a response to gravitational whispers from neighbors we can barely see, proof that no galaxy evolves in isolation. And somewhere in its glowing core lies a message. The universe's most brilliant displays often arise from collaboration, a reminder that even in the vastness of space, connection sparks creation. The ghost of Jupiter floats in the cosmic void like a shimmering soap bubble, its spherical shell of gas glowing faintly against the darkness, a celestial afterimage of a star's final breath. Officially catalogued as NGC 3242, this planetary nebula earned its eerie nickname not just from its pale, translucent appearance, but from its uncanny resemblance to Jupiter's disk when viewed through small telescopes. Yet this cosmic specter is anything but planetary. What we're witnessing is the outer layers of a dying star, expelled tens of thousands of years ago and still expanding outward at 19 miles per second, a delicate shroud that will eventually dissipate into the interstellar void. What makes the ghost of Jupiter so mesmerizing isn't just its haunting beauty, but the quiet elegance of its demise. Unlike the violent supernova of massive stars, this nebula represents a gentle exit, a sun-like star shedding its skin in a slow, radiant exhale. The nebula's symmetry is its most striking feature, near-perfect spherical shells nested like layers of an onion, each one a snapshot of the star's death throes. These layers aren't static, they're a stellar autopsy, revealing how the star pulsed and shuddered as it ran out of fuel, ejecting material in waves that sculpted this luminous cocoon. At the heart of this ghostly sphere lies the star's corpse, a white dwarf no larger than Earth, yet so dense a teaspoon of its material would weigh as much as an elephant. This smoldering remnant burns at a staggering 50,000 degrees, its ultraviolet radiation ionizing the surrounding gas and making the nebula fluoresce in hues of blue and green. But here's the cosmic irony: the ghost's brilliance is fleeting. Without fresh material to energize, the nebula will fade over the next few thousand years, its gases growing too diffuse to glow. The white dwarf, meanwhile, will cool over billions of years, dimming from blue to red to black, a diamond in the dark, its light gone but its mass enduring. This nebula challenges our perception of stellar endings. We often focus on the drama of supernova or the majesty of spiral galaxies, but the ghost of Jupiter reminds us that most stars, including our sun, will bow out quietly. Their final acts aren't explosions but transformations, turning their atmospheres into glowing shrouds that enrich the cosmos with carbon, nitrogen, and oxygen. Every atom in those fading layers was forged in the star's core over billions of years, now returned to space where it might someday form new worlds. Hidden in the ghost's delicate structure are clues to deeper mysteries. Why is it so spherical when many planetary nebulae boast intricate jets or butterfly shapes? The answer might lie in the star's slow, steady mass loss, absent the violent convulsions or binary companions that distort other nebulae. Its simplicity makes it a cosmic control group, helping astronomers isolate how single stars evolve without gravitational interference. Even the nebula's faint outer halo, a relic of earlier mass loss, offers a timeline of the star's long prelude to death. So when you gaze upon the ghost of Jupiter, remember, you're not just seeing a dying star. You're witnessing the universe's quietest rebirth, where endings are merely transitions, and even the most unremarkable stars leave behind ethereal masterpieces. It's a reminder that in the cosmos, not all light fades with a bang. Some stars exit with a whisper, their legacies written in gas and time. The Cigar Galaxy burns across the cosmos like a celestial flare, its elongated form glowing with the fierce light of newborn stars. Officially known as Messier 82, this starburst galaxy isn't just a pretty shape, it's a cosmic pressure cooker where stars ignite at a rate 10 times faster than in our Milky Way. What makes this galactic oddity so captivating isn't just its frenzied star birth, but the forces behind the frenzy. Nestled in the constellation Ursa Major and interacting with its larger neighbor, Messier 81, the Cigar Galaxy is a living lesson in how gravitational encounters can turn entire galaxies into stellar factories. Those radiant blue clusters strewn across its core aren't random. They're the aftermath of a gravitational tug-of-war. As Messier 81's gravity squeezed the Cigar Galaxy millions of years ago, shockwaves rippled through its gas clouds, compressing them into dense knots ripe for collapse. The result, a firestorm of star formation so intense, the galaxy's center outshines its outer regions by a factor of 5. But here's the twist, this starburst isn't sustainable. The Cigar Galaxy is burning through its gas reserves at a breakneck pace, like a wildfire consuming its fuel in one dazzling blaze. Within a few 100 million years, a mere heartbeat in cosmic time, this frenzy will fade, leaving behind a galaxy littered with stellar remnants and the heavy elements forged in its furnaces. What truly baffles astronomers is the galaxy's supercharged core. Unlike the quiet heart of our Milky Way, the Cigar Galaxy's center crackles with energy, its supermassive black hole feeding on the turmoil around it. But this isn't just any black hole. It's a cosmic power plant driving winds of charged particles that race outward at nearly 2 million miles per hour. These winds don't just shape the galaxy, they seed the intergalactic medium with heavy elements, proving that even chaos has purpose in the grand scheme of the cosmos. Hidden within the Cigar Galaxy's luminous disk are clues to deeper mysteries. Why do some galactic collisions trigger starbursts while others leave galaxies gasping for star-forming fuel? The answer might lie in the angle of impact. A direct encounter like the cigar's funnels gas inward, while a glancing blow can strip it away entirely. There's also the role of dark matter, whose invisible halo likely stabilized the galaxy during its violent encounter, preventing it from being torn apart entirely. Yet for all its fury, the Cigar Galaxy is a fleeting spectacle. Its elongated shape, more like a cosmic cigar than a classic spiral, is temporary, a snapshot of a galaxy caught mid-transformation. Over eons, gravity will smooth its contours, leaving behind a relic that future astronomers might struggle to recognize. But for now, it stands as a testament to the universe's creative violence, a reminder that even destruction can light the spark of new beginnings. So when you gaze upon the Cigar Galaxy's radiant form, remember, you're not just seeing a starburst, you're witnessing the aftermath of a gravitational dance where chaos and creation collide on a scale beyond comprehension. And somewhere in that glowing core, the universe whispers a truth we're only beginning to grasp, that even the most violent encounters can birth beauty, and that the cosmos writes its grandest stories in the language of fire and motion. The Bubble Nebula floats in space like a cosmic soap bubble, its near-perfect spherical shell glowing against the dark canvas of the constellation Cassiopeia. This delicate structure isn't some celestial accident, it's the handiwork of a ferocious young star, its winds carving a cavity in the surrounding gas with such precision, it looks like it was blown by the universe itself. At its heart lies SAO 20575, a massive star 40 times heavier than our Sun, burning so hot its ultraviolet radiation ionizes the nebula's outer layers into a brilliant blue-green hue. What makes this vista extraordinary isn't just its beauty, it's the violence behind its creation. That seemingly fragile bubble is actually the front line of a stellar hurricane, where winds racing at 4 million miles per hour slam into cooler interstellar gas, sculpting a shockwave so crisp it could pass for glass. Peer closer and the nebula reveals its contradictions. The bubble's western edge appears shattered, its symmetry broken by denser pockets of gas that resisted erosion. These imperfections tell a story of uneven resistance like a stream encountering boulders. The stellar wind molds itself around obstacles, creating turbulent swirls and finger-like projections. Yet even these flaws are fleeting. Over millennia, the relentless pressure of radiation will smooth the nebula's edges, either evaporating the stubborn clumps or pushing them outward until they dissolve into the void. This isn't a static sculpture, it's a dynamic battleground where light and matter vie for dominance. What's truly astonishing is how rare such perfect bubbles are. Most stellar winds create chaotic, asymmetric nebulae. Only under precise conditions does this delicate equilibrium emerge. The parent star must be massive enough to produce fierce winds, yet isolated enough that no neighboring stars disrupt the outflow. The surrounding gas must be dense enough to glow when ionized, but not so thick it distorts the bubble's shape. It's a cosmic Goldilocks scenario where every variable aligns just right to create this temporary masterpiece. But the bubble nebula's fate is already sealed. In about 10 million years, a blink in cosmic time, its central star will exhaust its fuel and explode as a supernova, obliterating the delicate structure it spent millennia crafting. Until then, the nebula will continue expanding at 60,000 miles per hour, growing fainter as it stretches into the interstellar medium. Like a real soap bubble, its existence is both breathtaking and ephemeral, a reminder that even the universe's most exquisite creations are fleeting. Hidden in this glowing sphere are clues to deeper mysteries. The nebula's interior isn't empty. It's filled with a faint, diffuse glow from gas heated to millions of degrees by the star's winds. This invisible furnace challenges our understanding of how energy transfers in space, showing that even empty regions can harbor extreme physics. The bubble's outer shell, meanwhile, acts as a laboratory for studying shock chemistry, the reactions that occur when supersonic winds collide with cold gas, forming complex molecules that might someday seed new planetary systems. The Bubble Nebula doesn't just showcase stellar power, it redefines our idea of cosmic artistry. Most nebulae owe their shapes to random turbulence or gravitational forces, but here, a single star's will has imposed order on chaos. It's proof that even in the vastness of space, individual actors can leave their mark, however temporary. And somewhere in that fragile, glowing sphere lies a lesson about the universe's dual nature, capable of both unimaginable violence and delicate beauty, often in the same breath. The Sunflower Galaxy blooms against the cosmic darkness like a masterpiece of celestial origami, its spiral arms folded into such tight, graceful curves they resemble the golden florets of its namesake flower. Located 27 million light-years away in the constellation Canes Venatici, this radiant spiral, officially catalogued as Messier 63, isn't just another pretty face in the galactic crowd. Its intricate structure reveals a deeper truth about the universe, that chaos and order aren't opposites but partners in an endless dance. Every twist of its arms, every knot of star-forming regions along its luminous tendrils, tells a story of gravitational harmonies playing out over eons. What makes the Sunflower Galaxy truly mesmerizing isn't just its floral symmetry, but the hidden physics behind those winding arms. Unlike the loose, feathery spirals of galaxies like the pinwheel, the sunflower's arms are so tightly coiled they almost seem to merge into a continuous disk, a phenomenon caused by density waves moving through its stars and gas. These waves don't just shape the galaxy's appearance, they orchestrate its evolution. As gas clouds encounter these invisible ripples, they compress, ignite new stars, and leave behind the glowing blue clusters that trace the arms like pearls on a string. The result is a self-reinforcing cycle. The arms create the stars, and the stars, in turn, highlight the arms. But here's the twist: the sunflower's beauty might be a fleeting phase. Some astronomers speculate its tightly wound structure suggests it's approaching the end of its spiral life, destined to one day smooth into a featureless elliptical galaxy. Others argue its pristine form indicates a rare period of equilibrium, where gravitational forces and rotational energy have found a perfect balance. The truth likely lies somewhere in between, a reminder that even the most stunning cosmic vistas are snapshots of an ever-changing universe. Zoom in closer, and the galaxy reveals its living pulse. The petals of this cosmic flower aren't static decorations. They're dynamic regions where stellar birth and death reshape the landscape. The brightest knots along its arms are H2 regions, vast clouds of ionized hydrogen where massive young stars bathe their surroundings in ultraviolet light. These stellar nurseries aren't randomly scattered. They follow the galaxy's underlying gravitational skeleton, clustering where the density waves have piled gas like snow before a plow. Meanwhile, the galaxy's golden core glows with the combined light of billions of older stars, their reddish hue betraying their advanced age. The sunflower also whispers secrets about cosmic kinship. Its structure bears an uncanny resemblance to other tightly wound spirals, like the Whirlpool Galaxy's companion or certain regions of Andromeda. This similarity isn't coincidence, it's a clue that galaxies, despite their unique histories, follow universal rules of structure and evolution. The same physics that shape a sunflower's floret's Fibonacci spirals emerging from growth patterns find echoes in these galactic arms, suggesting that beauty in nature, whether on Earth or across the cosmos, often arises from the same fundamental principles. Yet mysteries linger. Why do some galaxies wind their arms so tightly while others let them flutter loose? The answer might lie in their rotation rates, gas content, or even the gravitational influence of unseen dark matter halos. The sunflower's nearly flawless symmetry also raises questions. Most spirals show some asymmetry from past interactions, making this galaxy either unusually isolated or remarkably resilient. Perhaps the most profound lesson from the sunflower galaxy is one of perspective. From our distant vantage point, its structure appears frozen, a static bloom in the cosmic garden. But if we could speed up time, we'd see its arms slowly unwind and rewind like a grand celestial clock, its star-forming regions flickering on and off like fireflies. This dynamism reminds us that the universe's beauty isn't just in its forms, but in its motions, the endless, rhythmic dance of matter and energy that sculpts everything from the tiniest flower to the grandest galaxy. So the next time you gaze upon the sunflower galaxy's luminous spiral, remember, you're not just seeing a pretty arrangement of stars, you're witnessing a universal language of structure, one that repeats with variations from the quantum realm to the cosmic web. And somewhere in those golden arms lies an invitation to look deeper, to find the patterns that connect all things, and to marvel at how the cosmos weaves its tapestry of light. The Medusa merger writhes across the cosmos like a celestial gorgon, its tangled streams of stars and gas stretching hundreds of thousands of light years, a snapshot of two galaxies caught in the throes of transformation. Known formally as NGC 4194, this chaotic dance isn't just destruction. It's a cosmic alchemy where gravity weaves wreckage into new beginnings. As the galaxies spiral closer, their mutual pull stretches their structures into luminous tidal tails, river-like arcs of orphaned stars that will either drift into intergalactic space or eventually loop back into the merged galaxy's core. These filaments aren't just debris, they're stellar nurseries where compressed gas ignites into brilliant blue clusters, proving that even in chaos, the universe finds ways to create. What makes this merger extraordinary isn't just the spectacle, it's the timescale. Human lives are too brief to perceive galactic motion, yet here we witness a process unfolding over billions of years, frozen mid-stride by our telescopic lens. The galaxy's original spiral arms, now distorted beyond recognition, reveal how gravity rewrites galactic architecture with patient, inexorable strokes. The brightest knots along those streams aren't random, they're regions where colliding gas clouds triggered starbursts so intense they outshine entire galaxies. This isn't a collision in the traditional sense. Stars are so sparse that they'll never physically crash. Instead, it's the galaxy's gas that bears the brunt, its molecules slamming together at millions of miles per hour, heating up until it glows with X-rays. At the merger's heart lies the true enigma, a pair of supermassive black holes, each once the anchor of its own galaxy, now circling each other in a gravitational waltz. As they spiral closer, their gravity churns the surrounding gas into a frenzied vortex, creating a luminous accretion disk that may one day power a quasar, a beacon visible across the universe. This slow-motion tango could last millions of years before the black holes finally merge, shaking space-time itself with gravitational waves. Until then, their dance fuels the surrounding chaos, injecting energy that both suppresses and stimulates star formation in a delicate feedback loop. The Medusa merger also challenges our assumptions about galactic endings. We once imagined collisions as violent, apocalyptic events. Now we see them as creative acts, galactic recycling on the grandest scale. The same forces tearing these galaxies apart are also mixing their chemically distinct gases, forging heavier elements that will enrich future generations of stars and planets. Some of the merger's scattered stars may even become intergalactic nomads, drifting forever in the voids between galaxies. Others will settle into new orbits, their trajectories forever altered by this ancient encounter. Hidden in this cosmic wreckage are clues to our own galactic fate. Billions of years from now, the Milky Way and Andromeda will undergo a similar transformation, their spiral arms stretching into streamers before coalescing into a single, elliptical galaxy. The Medusa offers a preview of that future, not as a catastrophe but as a metamorphosis. Its tangled beauty reminds us that in the cosmos, destruction and creation are two sides of the same coin, and that every ending plants the seeds for something new. So when you gaze upon the Medusa's serpentine streams, remember, you're not just seeing a collision, you're witnessing the universe's endless capacity for reinvention, where chaos isn't the opposite of order, it's the raw material from which new order emerges. And somewhere in that luminous tangle, there's a silent promise: the cosmos never truly destroys, it only reshapes, recycles, and begins again. The red square nebula hangs in space like a cosmic jewel box, its near-perfect geometric form defying the swirling chaos we expect from stellar winds and explosions. This crimson enigma, discovered in 2007, isn't just another nebula, it's a celestial puzzle carved from dust and ionized gas, with symmetry so precise it looks engineered. At its heart lies MWC 922, a dying star shedding its outer layers in concentric waves. But here's the twist: instead of forming the usual spheres or spirals, the expelled material has taken on this uncanny square silhouette. The nebula's sharp corners and radiant cross pattern aren't just optical illusions, they're evidence of forces we're still struggling to comprehend. What makes the red square so bewildering isn't just its shape, but the physics that could create it. Most nebulae owe their forms to chaotic processes, supernova blasts, stellar winds, or random gas densities. Yet here, the outflow appears channeled, as if guided by invisible rails. Astronomers suspect the answer lies in a dense disk of dust surrounding the central star, funneling its ejections into conical outflows that, when viewed nearly edge-on, create the illusion of a square. Imagine shining a flashlight through a slitted mask. The beam forms a cross or rectangle. Similarly, the star's light escapes preferentially along two opposing cones, painting this geometric marvel across the cosmos. The nebula's vibrant hue adds another layer of mystery. Its deep red glow comes from hydrogen gas excited by the star's radiation, but the color's uniformity is unusual. Most planetary nebulae display patchwork palettes of oxygen, blue, and nitrogen red, yet the red square's chromatic purity suggests its chemistry is remarkably homogeneous. Some theorize the central star's slow, steady mass loss, unlike the violent convulsions of many dying stars, allowed for this even distribution, as if the nebula was painted with a single cosmic brushstroke. But the real intrigue lies in what the red square implies about hidden cosmic geometries. If one star can produce such a perfect square, what other shapes might lurk in the depths of space? Astronomers have since discovered nebulae with hexagonal patterns, even helical structures resembling DNA. These aren't mere coincidences, they're signatures of deeper ordering principles, where magnetic fields, binary star interactions, or even the rotation of the central star impose structure on chaos. The red square challenges us to rethink how form emerges in the universe, proving that even in the apparent randomness of stellar death, there can be precision. Perhaps most tantalizing is the nebula's fleeting nature. Like a sand mandala swept away by wind, the red square's perfection is temporary. In a few thousand years, its delicate dust walls will dissipate into interstellar space, erasing this geometric marvel forever. Until then, it stands as a reminder that the universe still holds wonders beyond our imagination, shapes so perfect they seem impossible, waiting in the darkness for us to discover them. The Needle Galaxy slices through the darkness like a celestial rapier, its edge on orientation transforming what should be a sprawling spiral into a razor-thin sliver of starlight. From our vantage point, this galaxy, officially known as NGC 4565, appears compressed into a needle's width. Its disk of 100 billion stars flattened into a golden line barely 3% as wide as it is long. But what makes this cosmic quirk so mesmerizing isn't just its unusual proportions, it's the hidden depths this perspective reveals. Those dark, jagged streaks bisecting the galaxy's glow aren't flaws, they're towering lanes of interstellar dust silhouetted against the combined light of countless stars. Seen face-on, these dust clouds would weave through spiral arms like shadowy threads. Here, they stack like layers in a cosmic parfait, exposing the galaxy's skeletal framework in a way no other angle could. Peering at the Needle Galaxy is like holding a vinyl record edge up. The music's still there, but the grooves become invisible. Its spiral structure, hidden from direct view, betrays itself through subtle clues. The central bulge glows slightly thicker and yellower, betraying the presence of older stars, while the disk's edges fade into a bluish haze, the telltale signature of younger, hotter stars congregating in the outer arms. Even the dust lanes hold secrets. Their uneven thickness hints at recent collisions with smaller galaxies, their debris now woven into the needle's fabric. This extreme perspective turns the galaxy into a cosmic cipher, where every shadow and gradient becomes a clue to reconstruct the grand spiral we can't directly see. What's truly humbling is how dramatically our view shapes understanding. The same galaxy, rotated just 30 degrees, would showcase sweeping arms studded with star clusters. From another angle, its barred core might dominate. The needle reminds us that the universe has no fixed appearance, only infinite permutations based on where we stand. It's a lesson that echoes across astronomy. Saturn's rings vanish when viewed edge-on, spiral galaxies masquerade as ellipsoids, and even supernova can appear deceptively dim if their jets aren't pointed our way. The cosmos is a master of disguise, its truths often hidden in plain sight, waiting for the right angle to reveal them. Consider the implications. If something as fundamental as a galaxy's shape can be so easily obscured, what other cosmic wonders might we be missing? Perhaps some elliptical galaxies are actually spirals viewed askew, their arms camouflaged by perspective. Those faint smudges at the edge of telescopic surveys could be needle galaxies of their own, their true natures waiting for sharper instruments or serendipitous alignment to unveil them. Even within the needle itself, there's more than meets the eye. Infrared observations pierce its dust lanes to reveal stellar nurseries, regions where new stars ignite despite the apparent thinness of the galactic plane. The Needle Galaxy doesn't just challenge our perception, it redefines it. That seemingly narrow sliver contains multitudes, star clusters orbiting above and below the disk like bees around a hive, rogue planets drifting between stars, even the faint glow of reflected light from countless unseen worlds. Its apparent simplicity is an illusion, a trick of geometry that underscores a profound truth. The universe rewards those who look beyond the obvious. Every time we train our telescopes on this cosmic needle, we're reminded that reality is rarely what it seems, and that the most ordinary-looking speck of light can unfold into extraordinary dimensions if only we change our point of view. The Southern Pinwheel Galaxy spins through the cosmos like a celestial fireworks display frozen mid-explosion, its arms bursting with the blue-white light of young stars against the Inkai backdrop of space. Known to astronomers as Messier 83, this grand spiral isn't just another pretty face, it's a stellar factory operating at full tilt, churning out new suns at a rate that puts our own Milky Way to shame. Nestled in the constellation Hydra and visible primarily from Earth's southern hemisphere, this galactic marvel serves as a vibrant reminder that cosmic wonders aren't evenly distributed. Some of the universe's most breathtaking sights remain hidden from half the planet's view. What makes the Southern Pinwheel truly extraordinary isn't just its star-forming frenzy, but the intricate patterns woven through its spiral arms. Unlike the graceful, sweeping curves of some spirals, M83's arms fragment into dozens of smaller strands, each lined with crimson nebulae and star clusters that resemble diamonds scattered on velvet. This feathery structure suggests a turbulent history, perhaps past encounters with smaller galaxies that stirred up its gas clouds like cream swirling in coffee. The galaxy's core glows with a golden hue, home to older stars that formed billions of years before their brilliant blue descendants along the arms. Yet even this ancient heart shows signs of recent activity, with dust lanes twisting in unexpected patterns that hint at a supermassive black hole's subtle gravitational influence. For observers below the equator, this galaxy is a crown jewel of the night sky, bright enough to spot with binoculars under dark skies, yet so rich in detail that large telescopes reveal ever deeper layers of complexity. Its southern location means many northern stargazers have never glimpsed it directly, a cosmic irony that underscores how much of the universe remains unseen depending on where we're born. The southern pinwheel doesn't just challenge our telescopes, it challenges our perspective, reminding us that Earth's orientation in space filters our view of the cosmos. Hidden within its luminous arms are clues to galactic evolution that northern hemisphere counterparts can't provide. M83's star-forming regions appear more numerous and compact than those in similar northern galaxies, possibly due to different environmental conditions in this sector of the local universe. Some astronomers speculate that the intergalactic medium here might be slightly denser, providing more raw material for star birth. Others point to the galaxy's unusual abundance of supernova 6 observed since records began, as evidence of a particularly vigorous stellar life cycle. Each explosion seeds the galaxy with heavy elements, enriching future generations of stars and planets in a cycle of creation and destruction playing out on a galactic scale. Yet the southern pinwheel's greatest gift might be the questions it raises. What other galactic marvels lie hidden below the northern sky's horizon? From the spectacular Carina Nebula to the dancing Magellanic Clouds, the southern heavens hold treasures northern observers can only study secondhand. This celestial inequality isn't just academic, it shapes our collective understanding of the cosmos, with entire classes of objects discovered and studied primarily by southern hemisphere observatories. The southern pinwheel stands as both a masterpiece and a messenger, its luminous arms whispering of countless other wonders waiting beyond our default line of sight. Perhaps most humbling is realizing this galaxy's light has traveled 50 million years to reach us, meaning we see it as it was when Earth's mammals were just recovering from the asteroid impact that wiped out the dinosaurs. That ancient light now falls on human eyes, connecting us across epochs to a structure that may have changed dramatically in the interim. The southern pinwheel doesn't just expand our view of space, it stretches our sense of time, offering a glimpse into cosmic processes unfolding on scales both vast and intimate. So the next time you consider the night sky's wonders, remember, the universe's beauty isn't distributed equally, and half our planet's view comes with celestial blinders. The southern pinwheel reminds us that perspective matters, in astronomy as in life, and that some of the cosmos' most dazzling performances are staged for select audiences only. Its very existence challenges us to look beyond our local horizon, both literally and figuratively, in the endless pursuit of cosmic understanding. The Statue of Liberty Nebula rises from the cosmic sea like a celestial colossus, its pillars of gas and dust sculpted into uncanny resemblance of torch-bearing arms and a spiked crown. This towering star-forming region in the constellation Carina doesn't just mimic Earth's iconic monument, it reimagines it on a scale that dwarfs human imagination, with its tallest structures stretching over 10 light-years high. What makes this vista extraordinary isn't just the chance alignment that creates this familiar silhouette, but the violent forces shaping it. Those radiant torch formations aren't static. They're battlegrounds where gravity and stellar radiation duel, their contours constantly reshaped by the solar winds of nearby massive stars. Peer closer at the nebula's robes, and you'll discover they're actually stellar nurseries, dense knots of gas collapsing under their own weight, incubating protostars deep within their folds. The crown's 7 spikes, towering columns of molecular hydrogen, their tops eroding under ultraviolet bombardment, while their bases shelter new generations of stars. This interplay of creation and destruction mirrors the nebula's earthly counterpart's symbolism, where Lady Liberty's torch represents enlightenment. The nebula's glowing crest shines with the literal light of newborn suns. The cosmic irony lies in the timescales. While humanity's statues weather centuries, these gaseous towers persist for mere millennia, a fleeting moment in galactic terms. Their familiar shape is a temporary illusion, a chance arrangement already dissolving under the relentless pressure of starlight. Yet within that brevity lies profound beauty. The same radiation tearing the nebula apart also makes it visible, ionizing hydrogen into the vibrant reds and blues that highlight its statue-like form. This celestial doppelganger invites a deeper question: what other earthly shapes might lurk in the chaos of Starbirth? From the pillars of creation's dragon-like silhouettes to the heart and soul nebulae's romantic contours, the universe seems to echo our iconography. Perhaps it's not coincidence but perspective our brains evolved to seek patterns, projecting familiarity onto cosmic randomness. Or maybe it's a reminder that the same physical laws shaping gas clouds also govern sand dunes and ocean waves, creating fractal beauty across scales. The Statue of Liberty Nebula ultimately transcends its namesake. It's not just a cosmic mirror. It's a dynamic workshop where nature's artistry intersects with human imagination. Every time we find such familiar forms in the void, we're reminded that the universe speaks a visual language we're only beginning to decipher, one where gas and gravity compose ephemeral masterpieces that resonate across cultures and cosmos alike. The hockey stick galaxy slashes through the cosmos like a celestial athlete's follow-through, its luminous core bending into a long, graceful tail that arcs across space for over 100,000 light-years. Officially catalogued as NGC 4656, this distorted wonder isn't just a galactic oddity, it's a fossil record of gravitational storytelling. That dramatic curve wasn't sculpted by chance. It's the aftermath of a gravitational tug of war, where a smaller galaxy's passage stretched its larger neighbor like cosmic taffy, leaving behind this shimmering signature in the stars. What makes the hockey stick so mesmerizing isn't just its playful shape, but the physics etched into every star along its tail. Unlike the orderly spiral arms of undisturbed galaxies, this structure is a river of stellar orphans, stars wrenched from their original orbits and flung into deep space by gravitational tides. The brightest knots along its curve aren't random. They're regions where gas compressed during the encounter, igniting fireworks of new star formation. Even as we marvel at its sporty silhouette, we're witnessing a galactic trauma frozen in time, a reminder that the universe's beauty often arises from violence. The galaxy's blade offers a masterclass in cosmic elasticity. Simulations suggest the tail's curve preserves a timeline of the interaction. Its tightest bends correspond to the intruder galaxy's closest approach, while the gradual straightening traces its retreat. Like a fingerprint in stardust, this arc encodes the speed, angle, and mass of the encounter, allowing astronomers to reconstruct events that unfolded hundreds of millions of years ago. Yet for all its scientific value, the hockey stick also sparks wonder. If gravity can craft this celestial sports equipment, what other whimsical shapes might lurk in the universe's depths? Hidden in its distorted form are clues to galactic resilience. Despite the disruption, the galaxy's core remains intact, a testament to how densely packed stars resist gravitational stretching. Meanwhile, the tail's faintest stars are slowly drifting away, destined to become intergalactic nomads. This slow dissolution mirrors the fate of all tidal tails, which eventually fade into the darkness, their stars scattered like cosmic confetti. The hockey stick galaxy challenges us to see the universe as both artist and athlete, capable of bending the rules of form and function into something unexpectedly familiar. Its existence proves that even in the vastness of space, gravity's touch can leave behind echoes of our own world, inviting us to find connection in the chaos. And somewhere in that glowing arc, there's a silent question. If we search deeply enough, might we find a cosmic soccer ball, a stellar boomerang, or galaxies shaped like constellations we've yet to imagine? The Diamond Ring Nebula glimmers in the cosmic darkness like a celestial heirloom, its perfect circle of glowing gas cradling a brilliant central star with such precision, it could pass for a jeweler's masterpiece. This planetary nebula, officially catalogued as Able 33, isn't just another stellar farewell, it's a masterclass in symmetry, where a dying star's final act unfolds with almost mathematical perfection. What makes this vista extraordinary isn't just its beauty, but the physics behind that flawless ring. Unlike the chaotic explosions of supernova, this structure was sculpted by patience, a sun-like star shedding its outer layers in gentle, concentric waves over thousands of years, leaving behind a luminous halo suspended in space. At the heart of this cosmic jewel sits a white dwarf, the star's exposed core burning at over 80,000 degrees. Its intense ultraviolet radiation lights up the surrounding gas like a neon sign, making the entire nebula fluoresce in hues of blue and green. But here's the twist. That iconic ring shape isn't solid, it's a bubble of gas expanding outward at 12 miles per second. A three-dimensional shell we happen to see edge on. From another angle, it might resemble a glowing sphere or a delicate soap bubble. The illusion of a diamond ring is a gift of perspective, a cosmic coincidence that aligns our view with the nebula's equator, framing the central star like a solitaire set in platinum. What's truly humbling is how ordinary this star was in life. The diamond ring's progenitor wasn't some celestial giant. It was a sun much like ours, unremarkable for billions of years until its final millennia, when it began crafting this masterpiece. As it exhausted its nuclear fuel, the star pulsed and shuddered, ejecting layers of its atmosphere in rhythmic waves. These ejections weren't random. They were shaped by the star's rotation and magnetic fields into near-perfect shells, like tree rings recording its death throes. The result is a nebula so symmetrical, it challenges our assumptions about stellar mortality. We expect chaos in death, yet here we find geometry so precise it rivals human artistry. Hidden in that glowing ring are clues to deeper cosmic cycles. The gas isn't just hydrogen and helium, it's laced with carbon, nitrogen, and oxygen forged in the star's core during its final phases. These elements, now returning to interstellar space, will someday seed new generations of stars and planets. The diamond ring isn't just a tombstone, it's a time capsule carrying the building blocks of future worlds. Somewhere in that expelled material might be atoms destined for rocky planets or even organic molecules, a reminder that endings in the cosmos are always beginnings in disguise. Yet mysteries remain. Why is the ring's inner edge so sharply defined, while its outer regions fade gradually into space? The answer might lie in the timing of the star's ejections. Later waves of gas could have collided with earlier ones, creating shock fronts that sculpted the nebula's crisp interior boundary. Or perhaps the white dwarf's intense radiation is evaporating the inner gas faster, leaving a well-defined rim. Even the central star holds puzzles. Its surface chemistry shows unexpected traces of heavier elements, suggesting it might have ingested planetary material during its death throes, a cosmic last meal before fading into oblivion. The Diamond Ring Nebula doesn't just dazzle, it invites us to reconsider stellar death as a creative act. Most planetary nebulae are asymmetrical, twisted by binary companions or magnetic fields into hourglasses or butterflies. This nebula's near-perfect circularity suggests a quiet, solitary demise, where the star's final breaths weren't disturbed by outside forces. It's a reminder that even in the universe's grand turbulence, moments of serenity can produce the most breathtaking beauty. So when you gaze upon this cosmic jewel, remember, you're not just seeing a dying star, you're witnessing a celestial legacy where a mundane sun transformed its final moments into a work of art. And somewhere in that glowing ring lies a silent promise that even the most ordinary things in the universe can, in their parting, become extraordinary. The Lundmark-Mellot galaxy drifts through the cosmic hinterlands like a ghost from the universe's infancy, its faint glow barely visible against the void. This small, irregular galaxy, often called WLM by astronomers, isn't just another speck on the edge of the local group. It's a time capsule. Isolated and untouched by major galactic collisions, WLM has preserved a primitive structure that mirrors how galaxies looked billions of years ago, before the era of grand spirals and elliptical giants. What makes this unassuming vista extraordinary isn't its size or brightness, but its stubborn refusal to evolve, offering us a direct line of sight into the cosmos's formative years. Unlike the Milky Way or Andromeda, with their intricate spirals and bustling stellar nurseries, WLM is a cosmic minimalist. Its stars are scattered like handfuls of sand tossed into darkness, with no central bulge or symmetrical arms to impose order. This chaos isn't accidental, it's a snapshot of the early universe, when gravity hadn't yet sculpted gas clouds into the elegant shapes we associate with modern galaxies. The stars here are ancient metal-poor relics, forged when the universe was still young and heavy elements were scarce. Their composition is so primordial, studying them is like analyzing cosmic ingredients before the first complex recipes emerged. But WLM's true value lies in its isolation. Nestled nearly 3 million light-years away, it's one of the few galaxies in our neighborhood that hasn't been cannibalized or distorted by interactions with larger neighbors. This solitude makes it a control group for galactic evolution, a rare example of how small galaxies might have developed if left to their own devices. Recent observations reveal another surprise. Despite its age, WLM is still forming new stars, albeit at a sluggish pace. Its gas clouds, though sparse, are pristine, unpolluted by the heavy elements that dominate larger galaxies, giving astronomers a glimpse of star birth as it might have occurred in the universe's earliest chapters. Hidden in WLM's faint glow are clues to one of astronomy's biggest puzzles: how small galaxies contribute to the cosmic ecosystem. Its dark matter halo, the invisible scaffolding that holds the galaxy together, is strangely disproportionate to its visible stars, suggesting these diminutive galaxies might be the universe's dark matter factories, far more massive than they appear. There's also the mystery of its sluggish evolution. Why has WLM resisted the gravitational dances that reshaped so many of its peers? The answer might lie in its orbit, drifting just far enough from the local group's heavyweights to avoid their disruptive pull. Yet WLM isn't entirely frozen in time. Hubble's sharp eye has caught pockets of blue young, massive stars that burn bright and die young, their explosions seeding the galaxy with the first traces of heavier elements. These sporadic bursts of activity hint at a slow-motion transformation, as if the galaxy is reluctantly stepping onto the evolutionary stage, billions of years behind schedule. It's a reminder that even in the cosmos, outliers exist, places where time seems to move differently, preserving fragments of a vanished era. So when you look at WLM, remember, you're not just seeing a small, forgotten galaxy. You're witnessing a cosmic relic, a living fossil that defies the relentless march of galactic evolution. In its faint starlight, we find echoes of the universe's humble beginnings, a whisper from a time when everything was simpler, quieter, and far more mysterious. And somewhere in its scattered stars, there's a lesson that progress isn't universal, and sometimes the most profound truths are hidden in the places we least expect. The Jellyfish Galaxy drifts through the cosmic ocean like a phantom of the deep, its delicate spiral arms trailing ghostly tendrils of gas that stretch hundreds of thousands of light-years into the void. Officially known as JO201, this mesmerizing structure isn't just a galactic oddity, it's a living demonstration of the violent forces shaping our universe. Those ethereal streams aren't decorative. They're evidence of a brutal struggle where the galaxy's interstellar gas is being violently stripped away by the pressure of intergalactic winds as it plunges through a dense galaxy cluster at nearly 2 million miles per hour. What makes this celestial jellyfish so extraordinary isn't just its haunting beauty, but the physics behind its transformation. The galaxy's trailing tendrils glow with newborn stars' pockets of compressed gas where the same forces tearing the galaxy apart are also triggering starbirth. It's a cosmic paradox, destruction and creation intertwined, where the shock of ram pressure heats gas clouds just enough to ignite them into brilliant blue clusters. These fireworks in the wake reveal how galaxies don't evolve in isolation. They're shaped by their environments, bent and sculpted by interactions we're only beginning to map. Hidden in the jellyfish's streaming tails is a timeline of its ordeal. The longest tendrils, rich with ionized hydrogen, mark where the stripping began millions of years ago, while shorter, denser filaments near the galaxy's disk show where the process continues today. Unlike tidal tails formed by galactic collisions, these streams are asymmetrical, sculpted entirely by the relentless wind of intracluster gas, a medium so thin it's nearly a vacuum by Earth standards, yet powerful enough to reshape an entire galaxy over cosmic timescales. This galactic metamorphosis challenges our understanding of resilience. The jellyfish's spiral structure remains intact at its core, proof that stars, spaced far apart, resist disruption even as diffuse gas is torn away. But the real surprise lies in the galaxy's star-forming efficiency. While most galaxies slow their starbirth as they age, the jellyfish defies expectations by producing new stars at an accelerated rate in its stripped regions. This unexpected fertility suggests environmental pressures can temporarily boost galactic creativity, like a cosmic pressure cooker forcing gas to collapse where it might otherwise drift undisturbed. The jellyfish also raises tantalizing questions about what else might lurk in the cosmic depths. If one galaxy can resemble a sea creature, what other celestial animals might be hidden in the telescope's lens? Astronomers have already spotted the Tadpole Galaxy with its elongated tail, the Stingray Nebula with its flaring wings, even the Seahorse Nebula's curving silhouette. These aren't just cute nicknames, they're reminders that nature's artistry repeats across scales, from ocean currents to galactic streams. Perhaps most humbling is realizing this galactic drama unfolds in slow motion. The jellyfish's plight isn't a one-time event, it's a phase lasting hundreds of millions of years, a transition that will leave it gas-starved and dimmer, yet possibly richer in heavy elements from its starburst swan song. Its fate mirrors that of many galaxies in dense clusters, where the intergalactic medium acts like a cosmic windstorm, gradually transforming spirals into gas-poor ellipticals over eons. So when you gaze upon the jellyfish galaxy's luminous trails, remember, you're not just seeing a pretty cosmic accident, you're witnessing a galactic rite of passage, where a once ordinary spiral is being remade by forces beyond its control. And somewhere in those streaming tendrils lies an invitation to look deeper, to imagine what other celestial shapes might be drifting unseen in the darkness, waiting for us to discover their stories. The snowflake cluster glitters in the cosmic night like a celestial ornament, its newborn stars aligned in near-perfect radial symmetry, a pattern so precise it defies the chaos we expect from stellar nurseries. Nestled within the depths of the Milky Way's Perseus arm, this young cluster isn't just a scattering of stars, it's a masterclass in cosmic geometry, where gravity and motion have conspired to arrange infant suns in spokes that mimic Earth's most delicate frost crystals. What makes this vista extraordinary isn't just its fleeting beauty. These stars are barely 1,000,000 years old, but the mystery of its formation. In a universe where star birth is often synonymous with turbulence, how did this structured elegance emerge? At first glance, the snowflake symmetry seems impossible. Most star clusters form from collapsing gas clouds that fragment unpredictably, birthing stars in ragged groups. Yet here, the cluster's namesake pattern suggests something far more deliberate. The key lies in the physics of its stellar nursery. As the parent gas cloud collapsed, it likely fragmented along filamentary structures, dense strands of molecular hydrogen where gravity's pull was strongest. These filaments acted like cosmic spokes, channeling material inward toward central nodes where stars ignited in near synchrony. The result, a stellar snowflake, its arms tracing the ghostly infrastructure of the gas cloud that birthed it. But the snowflake's order is already unraveling. These stars aren't fixed in place. They're racing outward from their birth sites at different speeds, their delicate arrangement destined to dissolve within a few million years. The cluster's current form is a snapshot of cosmic adolescence, a fleeting phase between the chaos of birth and the scattering of maturity. Infrared observations reveal even deeper layers, protostars still embedded in their dusty cocoons, positioned along the same invisible spokes like buds on a branching vine. This isn't just a cluster, it's a family portrait capturing multiple generations of stars in a single, transient moment of harmony. The snowflake challenges our assumptions about stellar siblings. Conventional wisdom holds that star clusters are born from free-for-all collapses, with stars ending up in random orbits. Yet here, the stars' motions suggest they inherited their orderly trajectories from the very gas filaments that birthed them like dancers following choreography written in the fabric of their nursery. This raises a tantalizing question. Could other clusters have begun with similar symmetry, only for time to erase the evidence? The universe might be full of such hidden patterns, their traces overwritten by billions of years of gravitational interactions. Hidden in this celestial snowflake are clues to a broader cosmic truth. Nature adores repetition. From the branching veins of leaves to the spiral arms of galaxies, certain shapes recur across scales, driven by universal laws of physics. The snowflake cluster's radial arms echo not just ice crystals, but the spokes of hurricane clouds, the petals of flowers, even the distribution of matter in the early universe. This isn't coincidence, it's convergence, where similar conditions produce similar structures, whether in a winter sky or the depths of space. So what other designs might the universe favor? Already, we've found star clusters arranged in strings like pearls, nested shells like Russian dolls, even three-dimensional fractals where small clusters orbit larger ones in repeating patterns. The snowflake invites us to look deeper, to search for cosmic fingerprints, shapes so fundamental, they emerge wherever matter organizes under universal forces. Perhaps someday we'll find a stellar whirlpool, a galactic spiderweb, or a nebula spun like a galaxy's silk. Yet the real wonder isn't just that these patterns exist, it's that we can recognize them at all. The snowflake cluster bridges the familiar and the alien, reminding us that the same physics governing frost on a windowpane also sculpts suns in the void. In its delicate arms, we find a silent promise. The universe speaks in shapes we're only beginning to decode, and every new pattern we discover is another stanza in an ancient interstellar poem. The Peony Nebula star burns through the cosmic darkness like a lighthouse shrouded in fog, its brilliance straining against the thick dust clouds that veil it from full view. Nestled deep within the Milky Way's central bulge, this stellar behemoth isn't just bright, it's one of the most luminous stars ever discovered in our galaxy, radiating with the energy of over 3 million suns. What makes this hidden titan extraordinary isn't just its raw power, but the way it defies our understanding of stellar limits. Even obscured by interstellar dust, its light heats the surrounding Peony Nebula into a glowing crimson halo, a cosmic signature betraying its presence like heat shimmering above a desert highway. Scientists estimate the Peony star's mass at nearly 100 times that of our Sun, placing it on the knife's edge of stellar possibility. Stars this massive live fast and die young, consuming their nuclear fuel in mere millions of years before exploding as supernova or even hypernova. But here's the twist: its luminosity suggests it might already be teetering on the brink of instability. The star's radiation pressure is so intense, it's constantly fighting against gravity's pull, shedding mass in violent stellar winds that blast outward at millions of miles per hour. This isn't just a star, it's a cosmic pressure cooker where the forces of creation and destruction wage an endless battle. The Peony Nebula itself acts as both curtain and canvas. Those swirling dust clouds that hide the star also serve as a projection screen for its brilliance, fluorescing where ultraviolet radiation excites hydrogen molecules into glowing pink and red. Infrared telescopes pierce the Vale, revealing structures within the nebula shaped by the star's fury, delicate filaments where shockwaves have compressed gas into eerie tendrils, and cavities blown clear by the sheer force of the star's light. It's a dynamic landscape, reshaped in real time by the star's unrelenting energy. What's truly humbling is how this star challenges the theoretical limits of stellar physics. Models suggest stars shouldn't grow much larger than 150 solar masses before radiation pressure overwhelms gravity. Yet outliers like the Peony star hint that the universe might have ways to bypass these rules. Some astronomers speculate it could be a binary system, its light amplified by a companion star. Others propose it's a rare supernova imposter, a star undergoing periodic eruptions that temporarily boost its brightness to deceptive levels. Every observation peels back another layer of mystery, proving that even in our own galaxy, the most extreme stellar phenomena remain just out of reach. Hidden in the Peony star's glare are clues to the galaxy's most violent cycles. The heavy elements in its winds, carbon, oxygen, silicon, will someday seed new generations of stars and planets. Its eventual death throes will likely produce a supernova so bright it could outshine entire galaxies, leaving behind a black hole or magnetar as its legacy. This star isn't just pushing boundaries, it's rewriting the cosmic rulebook, showing us that the universe's creativity far exceeds our imagination. So when you gaze toward the Milky Way's heart, remember, somewhere behind those dark clouds, a star burns with impossible intensity, its light a beacon from the edge of stellar possibility. And long after it's gone, its echoes will linger, a reminder that the cosmos thrives on extremes and that the most brilliant flames often hide in plain sight. The Tornado Nebula spirals through the cosmos like a celestial twister, its funnel of glowing gas stretching across space with eerie similarity to the violent storms that rake Earth's surface. At first glance, the resemblance seems uncanny, the nebula's tapered column, its writhing structure, even the way its debris clouds appear to swirl in the turbulent flow. But this isn't weather as we know it. The forces shaping this interstellar vortex operate on scales and intensities that dwarf anything our planet experiences. Magnetic fields trillions of times stronger than Earth's weave through the nebula's structure, channeling superheated plasma into corkscrew patterns, while stellar winds blast outward at millions of miles per hour, sculpting the gas into this monstrous, luminous whirlwind. What makes the Tornado Nebula truly remarkable is how it bridges cosmic and terrestrial physics. The same fluid dynamics that govern tornado formation, rotation, shear forces, pressure differentials play out here, but with star-sized consequences. At its base lies a dying star, its violent ejections colliding with interstellar gas to create shockwaves that organize the chaos into this eerie symmetry. Unlike Earth's transient tornadoes, this structure persists for millennia, its shape evolving as the central star's winds vary in intensity and direction. Infrared observations reveal even deeper complexity. The funnel isn't hollow but filled with intricate braids of dust, their patterns tracing magnetic field lines like iron filings around a cosmic magnet. This cosmic whirlwind invites a broader question. How many other earthly phenomena find echoes in the depths of space? The universe seems to delight in these parallels. From the jellyfish-like tendrils of RAM pressure-stripped galaxies to the snowflake symmetry of young star clusters, nature repeats its favorite patterns across unimaginable scales. Even the tornado nebula's smaller cousins, Herbig-Haro objects, exhibit miniature whirlwinds where newborn stars' jets plow through surrounding gas. These repetitions aren't coincidences but signatures of universal physical laws manifesting wherever similar conditions arise, whether in Earth's atmosphere or the interstellar medium. Yet the tornado nebula also defies simple comparisons. Unlike terrestrial tornadoes that draw energy from below, this cosmic version is powered from within. Its central star acts like an engine, driving the system with relentless stellar winds. The nebula's rotation isn't a single coherent motion but a complex interplay of gas streams moving at different velocities, some flowing inward, others spiraling outward. And where earthly tornadoes dissipate when their energy source fades, the tornado nebula's fate is transformation. Its gases will eventually disperse, enriching the interstellar medium with heavy elements while the central star cools into a white dwarf, leaving behind only echoes of its tempestuous past. Hidden in this celestial maelstrom are clues to how structure emerges from chaos. The nebula's twists and kinks map irregularities in the surrounding magnetic field, while bright knots along its length mark where shockwaves have compressed gas into stellar nurseries. Some astronomers speculate the entire system might be influenced by an unseen companion star, whose gravitational tugs could explain subtle asymmetries in the tornado's shape. Every new observation peels back another layer, revealing how even the most violent cosmic processes can produce fleeting moments of order. So when you gaze upon the tornado nebula, remember, you're not just seeing a pretty analogy. You're witnessing the universe's knack for turning fundamental physics into art, crafting familiar shapes from alien ingredients. And somewhere in those luminous coils lies a deeper truth that the same forces shaping dust devils on Mars or hurricanes on Jupiter also weave the grandest tapestries across the cosmos, proving that nature's imagination is boundless and its patterns infinitely adaptable. The cosmic reef shimmers in the void like an interstellar coral garden, its tendrils of gas glowing in neon pinks and electric blues, a celestial echo of Earth's most vibrant underwater ecosystems. This sprawling stellar nursery, officially known as NGC 2194, isn't just a feast for the eyes. It's a dynamic laboratory where the raw forces of star birth paint the cosmos with familiar beauty. The resemblance to our planet's reefs isn't mere coincidence, it's physics manifesting artistry across scales. Just as sunlight filters through ocean water to illuminate coral polyps, the ultraviolet radiation of young, massive stars here energizes hydrogen and oxygen atoms, making the nebula flourish in hues that mirror tropical waters. But where Earth's reefs rely on biological processes, the cosmic reef is sculpted by stellar winds and superheated plasma, proving nature's creativity transcends environments. At the heart of this cosmic aquarium lies a cluster of stellar titans, stars so young, they're still swaddled in the remnants of their birth clouds. Their radiation carves cavities in the surrounding gas, creating towering pillars that resemble coral branches, while shockwaves from their solar winds ripple through the nebula like underwater currents. The brightest regions glow crimson from ionized hydrogen, while cooler pockets of sulfur and oxygen add turquoise accents, completing the illusion of an alien seascape. But look closer, and the differences become as fascinating as the similarities. Those delicate filaments aren't static. They're stellar nurseries where gravity collapses gas into protostars, a process as relentless as coral growth, but operating at temperatures reaching thousands of degrees. What's truly astonishing is how this celestial reef challenges our sense of scale. The entire structure spans over 50 light-years, wide enough to swallow our solar system thousands of times over, yet its intricate details mirror formations we associate with handheld seashells. This paradox invites a deeper question. Why do such vastly different environments produce such eerily alike patterns? The answer lies in universal physics. Fluid dynamics, turbulence, and energy diffusion behave similarly whether shaping plasma in space or water on Earth. The same forces that arrange sand into dunes can sculpt gas into light-years, long tendrils, given enough time and the right conditions. The cosmic reef also serves as a reminder of our planet's cosmic connections. Many of the heavy elements that make Earth's reefs possible, calcium in coral skeletons, oxygen in water, were forged in stellar furnaces like those now illuminating this nebula. In a way, we're not just observers of this celestial aquatic parallel, we're products of it. The universe has a habit of rhyming across scales, from the branching veins of leaves to the vast cosmic web of galaxies. Yet beyond its beauty, this vista holds scientific gold. The reef's varied densities act as a time machine, showcasing different stages of star formation simultaneously. Some regions glow with the intense blue light of recent stellar births, while darker knots betray where new stars are just beginning to coalesce. Astronomers study these transitions like marine biologists cataloging species in a reef ecosystem, piecing together the life cycle of stars from infancy to maturity. The nebula's evolving structure even hints at how stellar winds might one day erode it entirely, an underwater cliff slowly worn away by cosmic tides. So when you gaze upon the cosmic reef, remember, you're not just seeing a pretty astronomical object, you're witnessing a universal language of form and function, where the same principles paint masterpieces in ocean shallows and interstellar depths alike. And somewhere in those glowing tendrils lies an invitation to wonder what other earthly patterns might be mirrored across the cosmos, waiting for us to dive deeper and discover them. From the haunting beauty of the pillars of creation to the violent elegance of colliding galaxies, these 42 cosmic vistas have taken us on a journey beyond imagination. Each one challenges our understanding of space, revealing the universe's boundless creativity and power. Some, like the delicate symmetry of the Cat's Eye Nebula, show us how stars exit the cosmic stage with grace, while others, like the Medusa Merger, remind us that destruction and creation are forever entwined. These aren't just distant sights, they're active participants in the grand story of the cosmos, shaping everything from the elements in our bodies to the very fabric of space-time. But here's the most exhilarating part. This is just the beginning. Every one of these cosmic wonders was once unimaginable until we pointed our telescopes skyward and dared to look deeper. The same universe that carved the Horsehead Nebula's silhouette and spun the Sunflower Galaxy's golden arms is still out there, hiding secrets we've yet to uncover. Perhaps the next breakthrough will come from an amateur astronomer's backyard telescope, a space probe's unexpected transmission, or a flicker of data that rewrites our textbooks overnight. The cosmos doesn't reveal its secrets easily, but that's what makes the hunt so thrilling. As you go about your day, remember that these marvels aren't just pretty pictures. They're invitations to wonder, to question, to stay curious. Whether it's the eerie glow of the Horsehead Nebula or the fiery heart of the Tarantula, each vista whispers the same truth: we're part of something far grander than ourselves. The atoms in your hands, the light in your eyes, even the screen you're reading this on, all of it was forged in cosmic furnaces like these. So what's next? Maybe you'll be the one to spot a new supernova, or maybe you'll simply step outside tonight and gaze up with fresh awe. Either way, the universe isn't done surprising us. If this journey through the stars has sparked your curiosity, hit that like button, subscribe for more deep dives into the cosmos, and let us know in the comments which cosmic wonder left you breathless. Until our next adventure among the stars, keep looking up, because the greatest show in the universe is always playing, and your front row seat is waiting.